started.
So what do you say
We
about
are
that?
live. We are live on YouTube right now. And okay, we're here at the Anti-Gravity Labs, Falcon Space, and we also have Wayne Ojala calling in from Fail Forward Research in Canada. Show yourself, Wayne. And we have
Hi, everyone.
Dejan Corovic,
Hi.
who is our professor emeritus out in the
No,
UK.
I'm not, but
No, not a professor, but he's a good guy to have around. He has some pretty interesting insights, and we're working on all different kinds of gravity modification experiments. Jeremiah Popp is also working on something similar to what Wayne is doing, and we hope to have him on in a moment. He's just actually working on the technology right now as we speak, so it's like we're trying to get everyone in here and get everything moving and just show you exactly what it is we're working on. So, Wayne, why don't you take it away and show us what we're doing?
All right. Well, yeah, me and Jeremiah have been stoking each other lately, back and forth, working on this. Well, there's a couple of patents that talk about the relationship between creating gravity fields and converging and diverging electric fields. And of course, they have all of the calculus and general relativity calculations and equations in the patents to prove that, or at least to mathematically model it, which is above our heads. However, it says in the patent that it's not. You don't need to know the math or understand the math to practice the invention. But basically, the invention involves. Well, in the particular patents we're looking at, involves making like a tube type of capacitor. So this would be the outside electrode, and there'd be an inside rod or inside electrode as well. And then on one half, you'd have, say, so this is the dielectric, but on one half would be, say, like a dielectric of higher K or higher permittivity than the other side. Or you'd have on one side, it would be a denser dielectric than on the other side. So the idea is that would create an asymmetrical force that would cause the capacitor to want to move in the direction of the denser dielectric material. So this is one I tried making. It didn't turn out so well. So there's more development to do with that. There's some challenges with it. But what I wanted to do, what this thing here is, this is basically the same thing. It's a cylindrical capacitor with oil dielectric. And so what I'm doing is I'm just charging it up to high voltage, probably about 70 kilovolts. And what I wanted to see if on the inside or in the center here, there might be some space-time distortion, or which causes gravity fields, curvature of space-time, according to conventional theories. So if there is, inside here, in an ideal cylindrical or spherical capacitor, there would be zero electric field in the center of a charged sphere, or in this case, a cylinder. So if there's zero electric field in there, then really nothing should be moving in here. There should be no attraction between this little bob here and the inside of this container, or the inside of this electrode. So what I'll do is I'll just flip this on, and we'll just see what happens here.
Are we trying this now for the first time?
Yeah.
Oh, wow, this is exciting. Can you show us the power supply as well, and like dive into that a little bit? Because
it's just the multiplier. I don't know what's coming out of here. I think it's somewhere around 70 kV, because I don't know what this thing puts out. Probably 10 kilovolts. I don't know. What do you think? It's a neon sign transformer.
Right. This is something that you've been that we were fed by. What was his name? Nam Tran, right? So this is.
I mean, I tried to make it like NAM, So I got the same number of stages here. I got a negative output one and a positive output one. This is the negative output one. So yeah, I mean, it's just a rough estimate. It's probably somewhere between 60 and 80 kilovolts. So this thing here is actually floating on top of some water. It's going to be hard to see with my camera.
Mm-hmm. Is there any reason why we're using water?
Yeah, well, my original thought was the water would ripple. I won't be able to, or you won't be able to see it in the camera if the surface of the water is rippling, if there's any gravitational gradients there. But it should cause the surface of the water to shift or ripple or something. But if I, just give me a second here, let me just readjust this. And then you'll see the bob move a lot more.
Well, you lost your video there.
Yeah, I turned it off for a second. Okay, so the bob is just suspended in air. And so I'm going to turn the power on right now. I don't know if you can see that, but there is some movement.
Yeah, we're seeing movement. Can you tell us which direction it's moving in?
It appears to be moving towards this way, towards the edge. And it seems to be related to how close it is to whatever. So if it's slightly off center, it'll move in the direction towards where it's closest. The closest direction to the inside wall.
So you might have to adjust those rubber bands over there.
Yeah, I can do that. It's no problem. I'll just move that over a bit. And you'll see it's much more dramatic.
It's very nice setup, very good solution for the setup.
I kind of just threw this together today, and so I mean there's probably some I could do a better job, but
you think you could do a better job, and then you go into the NASA lab where they spent $10 million to replicate this experiment or whatever, and you see them using the exact same rubber bands and dollar store parts, and then it dawns upon you that the people that are working for NASA are no different than you and I. They just they're just getting paid higher salaries. It's the only difference.
Look, I'll tell you one thing. I could watch up anything about Apollo mission to the moon 100 times, no problems. And they were going on about moon buggy. That was this little car which they used to drive around the landing site and all that. And you know how much that moon buggy cost them to make?
How much did it cost them to make it?
It cost them $68 million.
And this was in the 1960s too.
No, yeah, that's in 1960. But just a moment. All that moon buggy is just a folding bed. I think if somebody said $500,000, that would sound crazy large sum of money. It's just a folding bed. There is just an aluminum frame which is welded, and it has two joints, so folds in two places, and it has some wheels made of chicken wire, and 68 million. How do you even spend? How do you come up with the ideas how to spend money on that? It's just crazy. They totally overspend money in NASA. They have no control over themselves. It's just like.
Yes. Okay, so let's get back to the actual experiment. Show me those rubber bands again, okay? Dollar store parts.
Ready? Yeah, it is dollar store actually. It's dollar store rubber bands. All right, here we go.
And now with the stronger offset.
So, yeah, look at it So it's moving quite substantially there. You should be able to see that.
So that's all according to that patent.
This is not the patent. This is just my idea.
Oh, that's your interpretation of patent.
I know. Yeah, well, it's sort of an offshoot of the concept, but I wanted to test for what would be happening in the center of one of these capacitors, field-wise or gravitational-wise, or so. Yeah, I don't know. Like it, hard to say, right? Conclusively, what's going on there, but
I would say that right in the center, you have actually least action going on. You really need to be somewhere where electric field is very strong, because that space-time curvature is proportional to strength of electric field, and right there in the center, electric field is zero, so it's not very strong.
What's causing it to move then? What's causing it to move?
Oh yeah, that could be just maybe some small asymmetry in your setup. Maybe you're off center a little bit.
Well, yeah, it is off center, but like according to conventional, you know how a Van de Graaff generator works, right? Like inside that big metal sphere, the electric field, if you put a probe in there and you measure it, it's going to say zero, because all the charges on the sphere, inside the sphere, they cancel each other out and they repel against each other. So the net field in there is zero.
Okay.
So this is, geometrically similar, like this.
Yeah, but Van der Graaff generator does not produce gravitational effects in its center.
Well, how do we know?
We know from general relativity. General relativity, you could see it in that stress tensor. That relativistic effect is proportional to strength of electric field. So if electric field is weak, you get no effect. What is it called? Stress tensor.
You were talking about earlier about the Mach effect.
The thing is though, Dejan, if you think about this, so the net, if you measure the field inside, yeah, it'll say zero, but the field lines are still there, are they not? I mean, they cancel out, but they're still there. So you still have, the field would be converging at the point in the center of the sphere. So
yeah, I see what you're saying, but you will get, you would need to get where action is, and right there, because everything is in a balance. There is no action. It's a, how could I say, a minimum point.
So you're saying, I mean, yeah. So if there's a gravitational component, that it would be happening in the dielectric.
Yeah, closer to where the field is strong.
Yeah, I mean, and I agree. But I was just looking for something that might be happening, in this case, in the center.
Okay, I was collaborating for some time with this guy called David White, and he's physicist and he's specialist in general relativity. And he worked out these equations from general relativity for something which has a strong mass and for something which has a strong electric field. And basically, something like that is a lifter. Like, these little lifters, you have them all over the web, and they actually produce like ionic wind. And that lifter close to that wire, because that wire has a huge curvature, and huge curvature produce a huge electric field. So right there, very close to that wire, you have a electric field which is strong enough to actually produce gravitational effect. But he did differential.
Do you see the screen, Dejan?
Yeah, something exactly like that. But problem.
Very thin cross-sectional wire.
Yeah, very thin. Problem is you couldn't go too thin because if you put high voltage, wire will just explode.
No, that's not true. And I'll tell you why.
Tell me.
Just a second to flip this around. Because it turns out that on the very, very small scale, when you get your cross-sectional area of a wire extraordinarily tiny, what ends up happening is that the electron momentum becomes more significant than the actual particles within the wire. So the electrons will carry away the heat energy of the wire that conducted them with them as they leap off, sort of as a electron emission heated cathode effect. It actually takes some of that momentum of heat with it. So it'll cool the wire as it does, and anything that those electrons hit, which would be positive in comparison, will receive the heat that was lost by that conductor. So they're self-cooling if they're negatively charged. Opposite effect if they're positively charged. But you could actually use that to your advantage if you wanted a heated anode, for example.
But main thing about that experiment is it must be done inside the vacuum, because otherwise contribution from the ionic wind is too big, and contribution from electric field and gravity curvature is too small.
Well, now you're talking about actually the gravitational effect from the electric charges on the asymmetrical dipole orientation of that geometry, but that's an entirely different thing than lifters, which operate by ionic propulsion, which is a reaction force. So if you're talking about the existing gravitational force that's there between the two wires, it is amplified if the positive conductor is smaller than the negative conductor, but according to Brown and according to other sources, claimingly it is always towards the positive electrode. So for example, if you have a high enough potential between the two plates and you have a parallel plate capacitor, the force will be towards the positive side, whichever that's on. And if you want to reverse it, you just simply flip the leads around and you'll end up getting a force on the opposite direction. So it's an interesting thing to look for. You do need incredibly high voltages to look for it. And unfortunately, the nature of high voltage is that it affects surrounding objects and attracts to them, including the walls of your vacuum chamber. So that's a problem. The way to fix that problem when looking for electrogravitics is to design the thrusters or effect-producing devices inside of a Faraday cage that is at zero potential on the outside or at ground potential. So Nasikas actually addresses that with his Wavy capacitor paper and with another paper that he wrote, talking about how you should have a zero potential casing. Sort of like what Wayne's got there. Wayne's looking for something similar with a zero potential casing. And you should have an electric field inside that casing that's zero everywhere. But of course, that's not true, because when you have a scalar potential, it moves. Go ahead.
Jeremiah, did you see this little demo?
I seen the video of it and I was super stoked because it makes us question what's really going on inside of what should be a neutral area.
But did you see this thing move?
I certainly did, and I wanted to ask, is that AC on it?
No, DC.
It's NAM's replicator. And by the way, super exciting, Nam Tran is actually with us. And
Awesome.
This is the first time I've seen you in person, Nam. How are you?
I'm good. Can you hear me?
Yes,
we can.
We can hear you. All the way from Vietnam Airlines. How you doing, Nam? Let me show you. We actually built. This was Jeremiah's work, really. He replicated your device.
I saw this a long time ago, and Jeremiah told me that
we built it.
It doesn't work when the whole capacitor is insulated.
Yes. There might be some ionic wind effects going on. Oh, and Sean is coming in as well. That's what Dejan was talking about earlier, is the ionic wind effects and the need to test all these experiments inside of a vacuum chamber, which is why we have a vacuum chamber here at the lab It's right over here. We got this. It's the largest one I could find. It's about 16 inches in diameter. Nice size vacuum chamber, and about 18 inches tall. So hopefully we can run some experiments.
That is nice. Check that out, man. That's yeah. Stick your face next to that so we can get a comparison of just how big it is.
I have a pretty big
Dude,
face.
that thing is a big vacuum chamber.
It is a big ass vacuum chamber. Oh, and look at this. This thing weighs as much as my truck, literally. And we had to put new wheels on it because they were completely corroded. But that set me back like $600 just for the wheels alone. But totally worth it. Now I could push it all around the lab and hook it up to anything. Oh, there's this. It's like a weird little. That's probably from the epoxy or something.
Hey, thank goodness your building doesn't have the river running underneath it. I don't know how well that would hold up.
Yeah, this thing, if it gets stuck in a ditch, it can get really hard to move. This thing is massive. It has so much kinetic energy. Like if you get it going 1 mile an hour and it hits a table or something, it can crack wood at 1 mile an hour.
Absolutely.
That's how much energy this thing has, and we're running it off of the Kepco power supply. And Thomas Anderson is coming in. So Mr. Cool Glasses.
When is your battle station going to be fully operational?
So the Battlestar Galactica is in the works, and I'm pretty happy that I waited for the electromagnet to show up before building the chamber, because I realized the best way to build it is not going to be just to solder all the plates together. What I'm actually going to do is I'm going to 3D print plastic rectangles in the shape of the waveguide that I want, and I'm basically just going to press all of the copper plates against it. So this way, if I want to adjust any of the plates individually, you can do it in any direction. So expand it that way, and they're not actually attached permanently. And that's
clever.
Yeah.
Okay, if you want, is there a screen sharing here?
Yeah, you should be allowed to screen share.
Okay, if I could show you that equation which David Whitey derived directly from Einstein's general relativity, which relates to lifters, I could show you basically, because equation tells you what voltage you need to achieve 1g, and 1g is like equivalent of Earth's acceleration.
So can you do the share screen? Do you see that option? It should be in the center. Here, I just changed it so that multiple...
Oh, there it is.
Okay, I just have to change the setting, so you should be good now.
Okay. Do you see this?
Not yet.
Okay, there it is.
We just see your beautiful face.
Oh.
Okay, now it's starting. Started screen sharing.
Aren't you sweet, Mark? There you go. Yeah, it's starting. It looks like it's beginning to work here.
Okay, so this is do you see it like a 8.61 times 10 to minus 11 and then blah blah blah. And down here he has E equals 114 billion volts per meter. That's a electric field that you need to achieve to get acceleration of 1g.
Oh, come on, man. No, I don't know if that math is actually correct.
Of course it's correct. Guy is he's a physicist with degree in physics and specialist in general relativity. That's consistent with the density of black holes. So you don't get significant, even the neutron stars, which completely consist of neutrons, have very small gravitational effects. That's what we are talking about.
But Dejan, having a degree in physics doesn't mean that your math is always right. So I do.
Is that Is that a converging field, like a nonlinear field, or is that just a symmetrical, homogeneous electric field? Parallel field. Because that's important.
I don't really know, but
it's probably a parallel, homogeneous electric field. He's probably looking at it from just, the energy density of such an electric field being equivalent to, creating a gravitational field of 1G around it.
I would be inclined to agree with you, but I won't be able to confirm that without checking.
Yeah, that's my initial thought on it. I mean, I doubt, unless you could show me or prove that he's talking about fields that are
okay. I use this equation to then get some calculation for a lifter, and somewhere in this piece of paper I came up with just 2 billion volts, because if you are using very thin, AVG 30 wire, I did this a year ago, so I forgot all the stuff. But basically, voltage on a wire needs to be around 2 billion volts to get 1G. 1G, it will just lift off on its own. Just if you are doing it in a vacuum, you will get 1G acceleration upwards. But thing is, okay.
You know what? If you're in outer space, I mean, the vacuum is almost perfect. And
okay,
perfect vacuum is actually the greatest dielectric. Has the greatest dielectric. I think it's like the number.
Okay, we could stop sharing.
It was like.
How do I?
Can't remember the number. It was huge, like the number of megavolts per meter in hard.
Okay.
Vacuum.
You don't need the whole 2 billion volts to get 1G. You could get maybe 10% of that, and you will have a significant. So you could get away with what's the 2% of 2 billion, like 200 million volts, which is still bloody high. But these are the, what you are doing is possible, but these are the figures you have to achieve. These are the parameters you have to match. With accurate scale, you could possibly measure 1%. So then you will need maybe 20 million volts. 20 million volts is achievable.
What kind of density, space density are we talking about? Because, I mean, 20 million volt potential, you can have that between us and an asteroid, in outer space. Is that creating a gravity well? Is that...
No, that's on the surface of a very thin wire, because a very thin wire has a huge curvature, and that huge curvature is a factor.
So it's a near field effect. This isn't something that goes.
Yeah. It's a near field, definitely. So that huge curvature helps you.
Okay, well, let's talk real numbers then. So if we whittle it down, you got 2 gigavolts per meter, right, required for 1G acceleration.
Yes.
Okay, and so that would give us 2 megavolts per millimeter requirement to have that same 1G acceleration. And assuming we want to make a smaller device, and 2 million volts is not actually unachievable at all. But let's take it down even one step farther and say, looking at actual engineerable possibilities. Let's say that we only can do
2 million. If you could do 2 million, you are there. You will have something.
Let's put it this way.
We have 1 million.
200,000. And because we can do 200,000 volts in 1 millimeter, because we actually have a dielectric material that can take 200,000 volts in 1 millimeter. So we have a material that'll work for that as an insulator to get us that charge density. And still, we should be looking at a, maybe 1/100th or 1/10th of a G acceleration then on that device if we build it correctly, supposedly, according to this math then, right?
No, you won't be getting 1G, but you will get a fraction, significant fraction of that, measurable fraction possibly.
Right, at 200 kV instead of 2
I'm okay with
megavolts.
that. I'm okay with the measurable fraction. Jeremiah, are you referring to?
If we're talking about space travel, that's one thing. If you're talking like traveling in the vacuum of space,
yeah, we are.
Or if you're talking about trying to get off the ground,
we are just trying to prove that effect exists.
Exactly.
We are not.
Yeah, we're at the stage of striking two rocks together and trying to show that you can get a spark and make a fire. Therefore, we can make a rocket and get to the moon. That's like that's the level of like proof of concept to therefore we can build a Saturn 5.
But what I think that is going to happen. Okay, I'm not an expert on relativity, and I'm just learning physics as I go. So
why aren't you an expert on relativity?
Oh no, Dejan, you can't say you're no expert on relativity.
So if you try to move, you will have a less force. That's what you will observe. It won't fly.
But if you push it, it'll move a lot easier.
Yeah, that's what would happen. You won't suddenly see it attracting other objects or being pushed away from other objects. No, it will become, that's what I suppose. So it adds additional degree of complexity to experiment because you have to kind of measure force with which it can be moved. It's inertia.
Yeah, so putting things back into perspective, let's make this a little achievable. Jeremiah, you're talking about a plastic or a insulator that can hold back 200,000 volts at a millimeter. Were you talking about the ABA plastic that I showed you the other day, or you got something else in mind?
No, I'm talking about polypropylene. Polypropylene is a unbelievable plastic when it's formed correctly and when it has the correct grain structure, internal grain structure to hold an incredible amount of voltage. I mean, think about those pieces that I have. They're like, I should actually measure them. Let me grab the caliper. I'll do it right now. Heck.
HDPE is quite up there too. It's used as insulators on in the electrical industry. High density polyethylene, and that's the same material they use to make milk jugs and ice cream buckets, and it's a thermoplastic. It's a thermoplastic too, so it can be melted down and reformed.
Okay, I got it. So the piece of material I was working with, that crazy disc for the invisible wall, that's 0.2 millimeters thick, so 0.2 of a millimeter thick, and I have had 100,000 volts on that stuff.
Wow.
So that's what I mean by like polypropylene is a incredible plastic. And also if you're looking for commercial impulse capacitors, the best of the best, Maxwell's and Cornell Dupliers and whatnot, you're going to find, not surprisingly, polypropylene sheets.
I actually just picked up some of this plastic. It's ASA. I'm not sure if that is polypropylene, but it was recommended as a very high dielectric strength material, and like you mentioned, like Jeremiah just mentioned, we might have to play around with the printer settings to figure out the correct manufacturing process to get that maximum high K strength, the high strength dielectric out of this. But it's something we're going to work on with the 3D printer. I got it in white. They didn't have it in clear. That's something we're going to work on next.
But my understanding would be that you don't need the electric. You would just need a thin copper wire or thin steel wire, and because you don't want to suppress electric field. You want to create as much of it as possible. So the electric is not part of this particular experiment. You would just make this thin wire and put it in a vacuum chamber, and you would measure its inertia. So I don't think you need electric dielectric here. Maybe in some another setup, but not in this one. The time suggested.
So we got to test something like that under motion, or where it's accelerating.
Yeah,
in a circular motion. Like that.
Yeah, you have to measure how much force is it producing while you are trying to move it. I don't know how to set up that too big. That's how they measure weights in a space station, because in space station they don't have a gravity, so they are basically just bouncing on some lever type of thing, and then they're measuring inertia, and from inertia they're measuring mass.
I just wanted to tell you guys we do have a live chat going, and a guy named Peter Middleton mentioned that plastic thin films a few microns have a dielectric breakdown many times higher than their standard when they're measured at higher thicknesses. This is true. When you get a measurement for dielectric strength, which is the amount of voltage the material can take before there's a breakdown, the numbers are not linear, meaning that if you have a number for 1 millimeter and you go to 10 millimeters, you're not getting 10 times more. It drops off a bit. So the thinner you go, the stronger the dielectric strength is per millimeter. So
basically you have a law of diminishing returns.
Exactly. Well said. Yeah.
Okay.
There's a law of diminishing
returns.
returns.
Have you guys what are you going for? Are you going for something that can have normally like a negative triboelectric charge on it? Because like you got a negative 70 on styrene, but you can dissolve that stuff in just simple xylene you buy at the hardware store and pour it into a mold. And that xylene will absorb an awful lot of styrene before it even begins to gel. Like I showed Jeremiah this little real thin, in fact, actually it's still here. This stuff right here.
Oh, Tom, your video's off. Can you?
Yeah, I see that.
Get your video going.
This material here that's almost like, it's like a butterfly wing thick, just a real thin, like watery slurry, because I put a little bit of, just like styrofoam peanuts in it. He let it set so that the titanium dioxide will settle out of it that they put into it to keep it from breaking down from the UV, and then you've got pure styrene. But, I put, I think like 3 ounces of it, I was able to get about 2.5 pounds of styrene into it. So it was pretty thick, but it's not like the acetone. If you dissolve styrene with acetone, it seems to thicken up way too quickly, and it dries out too quickly too. So you end up with this gelatinous mass instead of it being a runny slurry that basically whenever it dries, it comes out crystal clear. So that way you don't have to worry about impurities, no bubbles, nothing like that. Of course, you have plenty of time. Then you can throw it in a vacuum chamber and vacuum it down to pull all the air out of it before it finishes drying up. I'd say probably about 3 inches per 24 hours is about the rate that it would dry out at. So based on just what I've done so far with it. So because the xylene is it's much slower at drying out. That's why you get the really smooth, clear textures. It doesn't get powdery or matte finished. But like if you put it inside of a Ziploc bag, it'll go right through the Ziploc bag and dry right out in a day or two. Whereas like if you put some acetone in a Ziploc bag, you'll still have some residue in there, some liquid residue, 3-4 days later. So it's very good at sliding through in between the molecular bonds to put it into. You gotta, if you want to trap it, you have to trap it with like glass and metal. So I use like an aluminum sheet stuck on the inside of the jar and then press that down onto the rim of the glass jar. And it does help to cool it so that way it doesn't build pressure, because it will still try to evaporate and build up pressure if it's sitting in too warm of a room. But, so basically it should be pretty good at basically working through the solid mass as it's evaporating and not cause any serious problems. I haven't had much problem either with shrinkage from it like you do with acetone when styrene dries out. I'm not sure what all else it will dissolve though. So I know it won't dissolve nylon. Don't try that. You need methylene chloride. Seems to be the only true solvent for that. It doesn't just soften it; it'll completely liquefy it. So, but that stuff dries like incredibly fast. So, I haven't tried it yet. But what I'm going to try doing is doing a mixture of xylene and the methylene chloride. That way, you can slow the rate. Once the methylene chloride has dissolved the nylon, then or polycarbonate because it works on both. Then go ahead and add the xylene to it to slow down its dry rate, so that way it doesn't, it doesn't come out with that crystalline like powder-like effect, so that a lot of it will end up basically just flaking off, and only the core of it being solid. That way, it should make the whole mass solid. So, and there's other ways to slow it down if you just basically restrict its ability to evaporate by creating a smaller chamber or something. So,
what kind of vacuum levels are we talking about?
What kind of what?
What kind of vacuum levels are we talking about?
To get the air bubbles and stuff out?
Is it just like a regular vacuum pump, or do you need to go?
Yeah, probably just a regular vacuum pump. Just make sure there's enough, I should say, negative pressure in order basically for, gas bubbles that might be dissolved, and it would basically try to escape to fill that void. There's, more propensity to move that way rather than stay in the solution. So.
Right. We actually have a new vacuum pump that I purchased on auction. It was $500 for this like $5,000 vacuum chamber, and it's coming in from San Diego. Actually, the great David Alzofon himself went and picked it up from the auction and shipped it over to us in the lab. And
molecular pump?
I don't remember the exact design. Jeremiah and I were looking over the specs, and he gave me the approval, said it was a good thing to have. But all I know is that it costs like $5,000. It's not the pump that you put in for the first level, for the first stage. It's like the one that you put in after you pumped out most of the air, just gets the last little bits out to really take you down deep. And we're hoping to get.
I take it you're not supposed to heat the thing to do this, like they do to help assist the evacuating the rest of the gas in like pitcher tubes.
I'm not sure. I'm gonna have to read the instruction manual.
If it doesn't have any instructions or any equipment for that, then it probably is a molecular pump. Those are quite intense. I definitely would like to have one of those.
I don't think it's a molecular pump.
One.
I don't think it's that level of vacuum, but it wouldn't be necessary for removing bubbles. This is more like for vapor deposition kind of stuff, and maybe running high voltage experiments when you want to make sure there's absolutely no
atmosphere to go into plasma state.
Yeah, no atmosphere to go into a plasma state, exactly. Also, I was showing you guys earlier before you got on, the electromagnet has arrived here at the lab, and
you didn't see my question on that, did you?
No, I did not see your question on it. What?
I wanted to know if that's wrapped coil or if those are stacked plates. Is there anywhere to basically like pump fluid through it to keep it cool?
Yeah, there is. Here, let me
then that's stacked plates then, most likely.
Yeah, it probably is stacked plates then, because there is these ports over here for fluid that comes in. These are a bit corroded. We're gonna have to replace them, but I don't see any need.
You should be able to take a neodymium magnet that has been completely demagnetized at room temperature, put it in between there, and pop it with that, and it'll fully magnetize it all the way up.
Oh, that's a cool idea.
It'll force the crystals to realign while they're in a cold state, which is how they make them basically to get the best ones. The crystals,
let me just
by making
ask
those
real quick, I missed that. What are we talking about? That sounds really interesting. I wanted to catch what you were saying, but I missed it just a little bit.
I was asking him initially, like, if he knew if it was coils on the electromagnet or if it was stacked plate. And then I asked him if it had like water inlets for cooling, and he said it does. So that means it most likely is stacked plates, which is what they use to be able to massively generate like the massive magnetic charges to force cold reorientation of the magnetic crystals in neodymium magnets. So,
what kind of magnetic field strength do you need for that?
Jeez, man, I don't know. I'd have to look that up. It's been a long time since I looked at it. I know it's got the Tesla name on it, so, but I don't know if it's like 2, 3, 4, if I'm thinking way out of the range, or maybe that's way too small. It's just something ridiculous. Like, you definitely don't want to stick your hand between there, because you could end up with some serious problems with it affecting the materials that are in your hand, like the water and whatnot.
I don't know if this magnet is powerful enough, but I have taken it up with just 100 watts of power, or actually no, I think it goes like 200 watts of power with the Kepco, and it was giving us 0.86 Tesla.
Well, they levitate frogs in a magnetic field because of the water in their body. So I'm thinking you could probably use like
that's like 7
water in it.
That's like 7 plus Tesla. That's like
see if it affects
it's not that strong, because you have an iron core there in that coil. You could see it as a tapered cylinder, and that iron core is limited
maximum saturation.
Through saturation to 2 Teslas. So you
have to have an air core, or do they use something different, like a nickel cobalt or something?
No, they are using superconductors for levitating frogs.
So like, what is it, like copper and niobium or something? The lamination, like they were using for what is it?
I think this is just the copper around the iron core, and that's all.
Right.
So you are limited to 2 Teslas. Whether the way they
God, it's too bad he can't pull that out and put whatever core he wants in it.
But it's not down to core, because no other material goes higher than 2 Tesla. That's how much you could achieve with any kind of material. After that, you need to use superconductors and air cores.
So do we need to get on growing some carbon nanotubes, some nice long ones?
Yeah, actually one could buy, I've seen a company selling superconducting tape, company from New Zealand, but you have to then do nitrogen and cooling and everything.
God, yeah, we need that room temperature level superconductors.
Well, actually, if they do sell superconducting tape, maybe they can create it with a slight curve, so we can make Nasicus version 3 thruster.
Well, yeah, you could definitely curve it. What version thruster?
Okay, so have you ever seen the Nasicus thruster? Or maybe it's the version 2 thruster. Yeah, I think it's the version 2 thruster. I'm sorry. Anyways, so in his original design, it's sort of like a tapered...
Spark alert. What's going on here?
What are you doing, Mark? What the heck is that?
That's not me.
What even is that?
This is Wayne. He's making sparks.
Oh, Wayne, what is that?
Whoa!
Sweet.
Oh, this is called plasticine. I had this crazy idea that plasticine, because I have kids, so I, find plasticine laying around. Like, this seems like the ideal material to make dielectrics out of, because it's easily formable, doesn't harden, and it just happens to be a good insulator too, apparently. So
it doesn't harden at all?
Well, no, it doesn't harden in air. So yeah, it's like molding clay. So they use it also. They use it in the automotive industry when they form prototype cars. They form them out of plasticine. So yeah.
Can you pour plaster over that and it won't affect it?
Pour plaster?
Yeah, like you build a wall around it, pour the plaster over it, let the plaster harden, then pull the clay you've got there out of it. That way you've got a mold.
Yeah, you could probably use this as a mold. Yeah. Okay. Actually, yeah, they do use it in molding as well.
I was thinking in Jeremiah's instance, he was talking about milling some molds for bismuth out of graphite, but there's probably other materials that could be used that would work just as well, that all he'd have to do is just make the form in a positive out of something like that.
Well, no, there was a specific reason I said out of graphite, and the reason was because I can pour the bismuth into it hot. And
it's going to stay in it then.
Well, it won't stay in it, no, but I can use it to form. Like I can basically pass a current through it because the carbon is conductive as well. But,
right, okay.
Yeah, there are properties of the carbon I was looking for. There was a reason for it.
Sorry to
That's
interrupt.
why I have it too. Yeah, go back to the.
Sorry to interrupt. I got my battery's about dead here, so I got to duck out. But it's been fun.
Thank you, Wayne. We appreciate the sparks.
You bet.
Yeah, thanks for showing that.
Nice talking to you, and thank you.
Bye for now.
Bye.
Okay, sorry, Jeremiah. I just had to cut you off there because we saw sparks. That was kind of cool. Back to what you were saying. Jeremiah, you're on mute. Did we lose you?
No, go ahead, guys. Go ahead. I got a lot of stuff going on here right now. I'm trying to make this wavy capacitor plate, and there's some some background noise. So it's perfect. What I was talking about was Nasika's version 3 thruster. Okay, so his V3 is the one that's little known. It's like his version 2, which is the tapered superconductor with a magnet at one side, and if you remove the magnet from it, it stops producing thrust.
Let's see.
His newest version, the V3, okay, it's a superconducting thruster, but imagine the superconductor as a coil where the coils are sort of like a tapered 45-degree cone. Imagine you cut the bottom and the top off the cone, and you just have sort of the center section where you have the one side slightly wider than the other in this taper, and you would pass a pulse current through it, and the expelled magnetic field from the superconductor would produce a radiated gradient field that would not be equal and opposite, and consequently a force would be felt by the body of the superconductor, which theoretically is capable of lifting its own weight. What are we looking at there? Or as far as I'm sorry, I got the video behind.
That's the graphite formation that I formed with the. Let me see if this shows up. Am I even at?
It's very interesting.
Let's see. I don't know if that's showing
Is that
up very
capped
well
on
there.
tape?
What's that?
Is that some capped on tape?
Yes.
You need to move camera up a little bit.
Yeah, we're looking at your 18650s.
Right. Yeah, there we go.
Oh, I have that same laser.
50 milliwatt?
Yep, 50 milliwatt. It's right here.
405, yeah. It's a good little laser.
No, mine's a 532, but the frame.
Oh, I've got a 250. It's like a 250 milliwatt green somewhere here, and then I've got another one I thought was going to be higher, but it came with like some little prism thing. So
actually, just the case is the same. The output power is 200 milliwatts at 532 nanometers. It's a green.
Yeah. See, that's only like 50 milliwatts less than the green one I've got. I'm really surprised by how much weaker the green is when it comes to burning and damaging stuff than a 50 milliwatt of the 405. And I would notice the difference too between my 2.5 watt 405 and the 15 watt 455 that I've got. The 15 watt barely does anything to MDF when it's not focused. That 405 fully unfocused with like almost a half-inch in diameter dot will still immediately start smoking MDF. So that's why I think that it was apparently working so well for them to turn the cap into that graphene foam. And the thing that I was watching, they were saying you could do it with other plastics, but the oxidation is really bad with the other materials, whereas this is able to handle being in an oxidizing environment and not lose the material, or it I guess break down to where it's just more graphite and not graphene related. So even though this still turns into this foam like structure. So
here's our 633. We got a 633 5 milliwatt helium neon laser. Yeah, the warranty expired in September of 1994.
So it might actually be older than some of the people that have hung out in here.
Most of this equipment is older than me.
Yeah.
Stuff was made back then, man.
I was in.
Here we go. This is what
I was in kindergarten when this was manufactured. When it was out of warranty.
You are ready for when aliens turn up.
There we go. See if I can get some of this to burn so you can kind of see at least. It's a really small line, so it took a while for me to build up that little area, but I was smelling it, so like, okay, it's working, so I'll need to get a wide enough area so I could actually get my multimeter tips on it so I could see if it's got a, actually forming a graphene material so that it have some conductivity and not like, just discoloring it or something. So, but there is like, it's, in the mega ohm range, but the Captain itself, no conductivity at all. So, it's infinite resistance. You touch on the black part, gives a readout, and it doesn't easily break down either. It's pretty tough. So.
Jeremiah, you were also working on getting some graphene plates. How's that working for you?
I did mess with a lot of different formulations using the graphene platelets in formula with other things, and just letting them dry out. The main purpose there wasn't to form a structural material out of the individual pieces, but more so to use the graphene and its high electron velocity as an electron donor for the material. So it's just continuously mixed in the entire mixture. I actually sonicate the whole darn thing to get it really contagious.
Oh, and that's with the that little 100-watt sonicator that you took from the lab?
Yep, that certainly does the trick, man. No problem.
I was talking with the people out in Tachyon Aerospace. They mentioned that sonicators get a lot more advanced than the ones that we have, and that certain frequencies are used for certain materials. He wouldn't elaborate much on that call. I think we need to do a private call with him to get those exact frequency numbers. But apparently, if we could have a wide range ultrasound vibrating systems that we can tune into certain frequencies, that would be a key piece of lab equipment moving forward with the material science part of this.
Sorry, for what purpose?
There is just so many things that you can use these sonicators for. It's not just about moving, separating beads of material around in an epoxy. There's certain material characteristics that change at certain frequencies, at very specific frequencies. I don't remember everything offhand. We had one of those conversations where you talk to him for half an hour and he dumps, a year's worth of research in your head, and it all just comes in one ear, goes out the other, because you can't absorb it all. But it was really mind-boggling, the amount of stuff that they've learned. And the sonification and the specific frequency ranges for certain materials allow certain things to bond, such as we were talking about getting the bismuth. No, not the bismuth. We were talking about getting barium titanate mixed inside of mercury. And there's a specific frequency for that as well. So,
you are talking about mixing materials which are otherwise impossible to mix.
Yes. It's material science, really.
Material. That's so interesting. I never came across with that. But that's and what are these people, a company or just
they're more than just a company. They're actually getting they're putting the paperwork together to become the official space agency of Malta. Now, Malta is an island. It's part of the European Union. It's out in the middle of the Mediterranean. They didn't have a space agency, so they didn't have any investment in rockets. And Tachyon came along and said, hey, we're going to do our anti-gravity stuff, and you'll get 10 million euro from the European Space Agency. And, all the politicians are super excited about getting money. So that is, what's happening. And they're literally starting and writing their entire... They got to write the laws on regulating their industry. So it's pretty much an open plate. I heard SpaceX was in talks with Malta at some point of becoming their space agency. That didn't happen. But it was a great opportunity that was taken up by the anti-gravity field researchers. And it's something
one of the reasons I'm doing math is because it's easier to get the grant money.
That's my squibbling right there with my hand earlier. You could tell when it was really ablating because, and it had gone over because it gets really super bright, like orangish pink, because you're basically lasing, just pure carbon. So it's just basically causing a bunch of black body radiation instead of it basically releasing energy from what's burning off.
Can you focus the camera a little bit? We're out of focus there.
Yeah, I haven't switched over. I had to force it to focus like this because their intelligent software keeps trying to basically focus on things I don't want it focused on. But yeah, that grayish like area, that's the stuff that ablated just a little bit ago. So unlike the, I mean like that, but I did that earlier. All of that's more ablating too. I've got, like I said, I need to set it up on the laser engraver and test to see if he's, his 405 that he used is maybe not the only frequency you can use, because I'm pretty sure we can probably use like a 10 or 15 watt blue laser too to do the same thing and create whatever pattern you're trying to make.
I'll let you know in about 30 seconds.
You trying it?
Yep. I just got to find 2 fully charged lithium-ion batteries, which I'm hoping are in my Bandura experiment box.
I was going to say, if it was going to give me too much trouble, I was about to pull this out.
Well, go ahead, man. You might have better focus on that thing anyways.
It's a 500 watt 405, so it's basically 10 times more power than this. Not what we bought, because when we bought this thing, myself and the guy in Dallas that I do research with, this was supposed to be a 2500 watt. And when it got here, it was literally a fifth of the power. So because he doesn't ever check anything, it took that long for me to get down there and look, and I saw that it was basically less power.
Did you just say 2,500 watts?
2,500 milliwatts. The other one's 2,500 milliwatt.
Oh, milliwatts. Okay.
For 405 nanometer, though, it's like in the very top end of the UV spectrum, because there is some that's like just below 400 nanometer that comes out of it. It means that you end up with basically your clarity when you're striking something with it, like that laser that you got with the helium in it. You get a much cleaner dot because it appears to have more control over the frequencies that it releases, whereas this stuff has got a whole host of frequencies. So,
well, that's blinding. Geez, I wish I had some goggles around here off the convenience. I got some goggles for specifically this. I don't have them here for some stupid reason, but anyways, okay. Well, let's see. What can I do here? Let me get on video, and I swear I burn my cam out.
Take a chance blinding yourself with that, man.
No, don't worry. This is quite exactly as dangerous as you think it is. This is the laser.
Oh, that thing is dangerous.
And it's Art Deco laser, not just a laser.
Oh, indeed. Of course, it has to have, it has to have the stylized steampunk look, because that is definitely the look.
I think I've seen that before.
Yeah, here's a piece of cap.
He was lighting cigarettes and green tobacco with it.
Yep, here we go.
Yeah. Oh, yeah.
Well, that didn't take long, did it? No.
No.
Wow.
Get your multi-tester out now.
Okay, give me a second. In fact, let's just do something. Let me just defocus and see if I can do a wide area here.
That'd be interesting. Yep.
Well, it certainly didn't work the same,
How much wattage is that thing?
7.
7 watts?
Yes.
What frequency? That's a 455?
Correct.
Ah, okay. All right. I don't know. I tried melting solder with the 455 I've got, and it didn't really do much work on that.
That'll definitely melt solder, no problem.
Does it?
Oh, yeah.
I was like, because the 405, the 2.5 watt one I've got, it instantly just destroyed it, and it vaporized the rosin core that was in it to where there was no smell like you get whenever you're soldering, that rosin smell from the smoke. Nothing. It literally completely broke all that stuff, all those aromatics down until they were just base molecules. Thing is, though, I don't know what the 405 will do, but I was able to do nothing with the 455 nanometer on copper. So I think anything that I was going to use it for soldering, I'd have to tin everything first, and then I'd be remelting the tin, as well as the tinning on the legs or anything that I'm soldering to it. So, because I was thinking, automated soldering system.
Well, I'm sure that must be touching the copper layer underneath. I think I have to take this. Well, if I do take the tape off, I'm going to bend it.
You put it on copper?
Well, the copper has a coating on it as well, but it probably burned off. I mean, I'm struggling with the leads right now. Basically, I'm just going to touch these and on here and see what we got from the side.
Lay them on.
You can just call out the read numbers.
Yeah, there I got readings in the megohms, but
yeah.
There we go. I got 1 point. Well, let me see. Am I getting conductivity? Yeah, see, it's not conducting quite as well. I got to take that tape off there. I can actually see a little piece. Let me see if I can get this on cam. Okay. I'll stop shaking around, see if I can get my video to focus. And check this out.
Wow.
See if I can pick this off. Yeah, it came, these pieces of carbonized material, they're actually coming off, like they're detached, and some of them are actually peeling off. Some of them did peel off as the stuff inflated, so there is an expansion, I guess, that explains the exfoliation, doesn't it?
Yeah, for sure. I'd have to find out what his settings were so that we could basically try to replicate exactly what he did, because he was making the little finger-style mini capacitors.
Oh, wow, I tried to take that off, but apparently the...
Yeah, it's destroyed. You destroyed the glue, it looks like, for the most part underneath it, too. There's very little bit left.
Yeah, I have to retest that on some non-conductive material, so let me try that experiment again with something that's not conductive.
Right.
I guess like that.
You should be able to use a piece of clear glass, clear plastic, too, because that laser should go
clear
right through
glass
it without doing anything to it.
No, clear glass is the perfect solution. It is.
Well, my thought initially, because he talked about the oxidation, was to put whatever you're going to ablate on a piece of clear plastic or glass, and then ablate it through the glass with something over it from behind, so that way no atmosphere can get to it.
Well, the trouble with that is we're going to have the adhesive side to be the facing side.
Right, if you're using Captain, but he was saying you could use anything if you could control, like get rid of the oxidation atmosphere. Like you could use styrofoam or box tape or whatever for it, but those things were more prone to basically breaking down if there was an oxidation variant available, like if there's oxygen in the atmosphere. So if you trap it between two objects, though, and you can strike it from the inside with the photons, then you should be able to basically make the stuff up from the back side of it. Because I'd heard some people were using spray paint, different types of spray paint and whatnot too. So the only trick I see with it is that because you're shining through a clear substance, because you're using a laser that is basically transmissive to the material, you'd have to use something that's doped with something that would absorb that light to generate the power in it that you need, instead of it continuing to pass through.
Okay. Jeremiah, give me a second. Let me spotlight you. Okay, we are watching you live now.
That's burning through the glass, so from the other side.
It's not fair. It's a lot easier for you to do this with a fucking lightsaber.
Well, why not? And let's grab the meter I just dropped, and we'll pop that thing back up there. I'll turn that sideways because I don't give a damn.
Right? You don't want to shine that in the sky at night. They'll be able to tell exactly where the hell you're at and come right down there to arrest you.
Jeremiah, why don't you close your messages in the background? We can see all your stuff going on your computer.
Oh, yikes. Yeah. Thank goodness it was everything that I typed.
We don't want to see your furry porn.
Oh, jeez. Is that what you're into?
Hey, I'm watching YouTube videos. I've run across all kinds of stuff people talk about, so I know what to use whenever I'm trying to get on to somebody.
Okay, Jeremiah, you're going to call out the numbers. What are we seeing there?
I will as soon as I see them. That ain't conductive.
I wonder if maybe it's too much power. You don't want to get that. You shouldn't have to touch that close.
Oh, geez, 230 ohms.
Oh,
okay,
wow.
Yeah, because he had like 1 and 2 inch long
60 ohms.
capacitor fingers that were working. So
35 ohms.
Wow.
Awesome. Yes. So now you just need
450 ohms.
the dopant to basically lay electrolyte and something to hold it on there to make some power storage units.
So what we have learned is that it works much better when you burn it from the surface without the adhesive. Maybe oxygen is required for the process.
Might be. The other thing too that I'm thinking is that means that you should be able to use something to absorb the photons to add to starlight. That way you can paint the starlight onto whatever you want, and then it's basically an expanding foam too. That's how it's able to basically stop an egg from being cooked while using a blowtorch to it. If you keep heating it after everything has been completely expanded, then the heat will soak right through that graphite that's formed all over it and right into the egg and end up cooking it. That's why old dude never really showed it for very long. Once it got done foaming up, then he cut it and let everybody just think, oh yeah, it would keep the heat from going in almost forever. It's like, no, it's not aerogel.
Yeah. Exactly. It is good for saving you from a fire and getting burned immediately, but ultimately won't save you from the heat.
Right.
It's
well,
just
this is the thing, though.
Delaying system. It's not actually an insulator per se.
Well, right. But this is the thing, though. Because it's a foam, I think it probably would be better at resisting thermal penetration than the materials that we normally use for TEGs. So I've been, that's my one of my plans for that is to test to see if I can make some positive and negative semiconductor dope, effects by doping it before burning it while it's layered together, to basically see if I can generate some TEGs that have a higher range of, thermal difference that you can get from one side to the other. So instead of this little like 60, 70 degree differences,
Right, exactly. No, I hear you.
I'd like to get down to where we can almost get like liquid nitrogen, with something like that.
My buddy's been messing with those. He's got a force stack that gets pretty damn cold. He can make dry ice on it, no problem. So I know he's getting into at least a decent range.
I was gonna say,
what's that?
Oh, I was gonna say, if you can really push that temperature down and it doesn't take much power because it's more efficient, it'd be a lot easier for cooling things like what you were trying to do the other day when you were pouring the liquid nitrogen and to try to drop the temperature. That way you could get those superconducting effects without all the headaches that normally come with it that have restricted it from being, say, inside somebody's PC, right? I mean, we're not going to have quantum computers in our PCs because it requires these temperatures that require liquid nitrogen or liquid helium or something, But if we can electrically produce that by pushing that heat out and refrain it from going back in using aerogels and whatnot, then you've reached the level where you can put that in somebody's house or in a starship or something like that, where it's sitting next to you. It's not like in a big, you got to have something the size of like a starship and it's down in the bowels somewhere hidden away with, a bunch of equipment just to keep it cold enough in order to be able to use it for whatever it is you're using it for.
We would really need a TEC that operated in a fundamentally different way than the junctions we have now, because they unfortunately develop quite a bit of heat as a consequence of their operation. So we want something that's a true, a heat pump in the truest sense, if it's even possible.
Right.
We do need a better technology for that, though.
Right. I was going to say, we probably need to investigate the thermal diode
yes.
tech that I was looking at, using vacuums and dual layer material where one side reflects all of the thermal energy that's generated. So you have to have black body radiation that's in the visible spectrum to actually poke through the coating that's on the second side, which can be eliminated by just fully coating it. So
thermal electric converters are literally the holy grail of free energy production. And if we can achieve
being able to take heat and turn it back into something useful. Yeah. Rather than just waiting for it to move from point A to point B and getting some energy from it.
Amen.
Yep.
Maxwell's demon.
I'm telling you.
Done.
This material right here. Wait, let me see if I can get it.
Dejan, you're right. It has been done. It just hasn't been perfected.
Right. Yeah.
It's done with the diodes. I don't know how they make it. But I was watching this Colonel of American Army, and he worked in a procurement for some big military places. And he was giving a whole lecture explaining about these diodes, which are really, really
It blocks the
small.
light.
But they could convert any type of heat into electricity, even when they are in outer space. As long as you are above absolute zero, they create electricity. And he was talking about them making a factory in India for like $2 billion US and starting to produce this. And they are supposed, these units are like exactly the size of mobile phone battery. And apparently they are going to replace mobile phone batteries and they are going to last forever. But apart from his lecture, I never heard any more about it. Although he was talking about, he said that they are actually in the process of building a factory. But it's completely workable because technology, because you have these 0 point fluctuations, and all that the diodes are doing, they are channeling energy in one direction and accumulating it on output.
It's literally Maxwell's demon. One way. If you can get the
Maxwell's
Brownian
demon,
motion going just one direction, because heat is essentially just movement of molecules. If you can just move an atom from one point to the other, stop it from moving back, or capture the electron, you create that potential, capture that energy, and make it less movement by going through. You just converted heat energy directly into electricity. What is the electricity that enters your home doing? It's basically
it's making heat. Whenever
basically
it gets expended as light or whatever else, it ends up, the end result is eventually that degenerates down and decomposes down into waste, random thermal energy.
Exactly. You're turning it into heat.
Did you notice that? No conductivity one side, plenty of conductivity on the other side. This is a bi-layer piece of material. There's an aluminum coating on one side, which will reflect all infrared photons that strike it. The other side is clear to us. To infrared radiation, that is solid black. It will absorb right into it and heat up that material until eventually it will end up basically creating black body radiation on one side or the other. If it ever exits this side, which you have about a 50% chance. This is just a space blanket, mylar with aluminum aluminized coating.
Okay.
Right. Basically, anything that exits the side that has the silver coating, if this is inside of a vacuum, that thermal energy can never re-enter this piece of material. Like I said, until you push so much heat into a chamber that's on the other side of it, that it starts releasing visible photons, because they're small enough with this material. They'll go between the little tiny dots of aluminum because of the gaps being small enough for visible wavelengths, but not small enough for an infrared photon to pass through. Because of the length of its waveform, it makes it too wide to go through. So you just need a vacuum in between each of the layers, and every single layer is going to create an effect where basically the photons of heat can only go one direction, and you can't transmit the heat any other way except as photons through a vacuum. So, at least as far as we know so far. So, what I've done is I've taken just this stuff, 2 layers of it over my window, and left the bottom window exposed. And in 10-15 minutes, you can put your hand on the back side of the window that has this stuff on the outside. With the 2 layers have a small gap between them. So we're just talking about the vacuum level where like every 1,000 parts has got gas particles in it, meaning 1 atmosphere pressure, right? You put your hand on the back side of that window and it has already dropped down to like anywhere from 1 to 3 degrees cooler than the house is in here. Whereas the window that's still exposed is still hot enough you'll burn your hand on any part of it that basically is not completely clear. And then the clear parts are still good and warm to the touch. So, I mean, I think there's a pretty good potential to use that sort of technology because it's very lowbrow, as opposed to the technology that might require, manipulating individual molecules and whatnot. This is easier for somebody to implement rapidly if they need something to do, some thermal pumping that's passive. The heat itself is the energy that causes the pumping action.
That's amazing. There's a guy in the chat, Peter Middleton, who I mentioned earlier. I really would love to get him on this Zoom call. He actually wrote a paper on a research disclosure paper about an excellent new way of approaching the challenge of producing cooling and electrical energy at the same time. Basically, it means turning on your air conditioner in the summer, and instead of it consuming energy and pumping heat outdoors, it's actually creating electricity in the summer.
Right.
And this is the holy grail of science, because it will of power generation, at least, because everyone's concerned with global warming. Now we can get rid of the power plants and cool off the planet at the same time by creating this energy.
Actually, you only cool the planet if you're using the energy to do something that is endothermic. Like if you're making molecules that will release heat whenever they're decomposed, that'll store that heat until you decide to burn them.
And
so
you know what you do with that?
You can store that for solar, solar minimums when it gets too cold, and release that heat back in the environment to keep it from getting too cold.
Or you can do is, since the ocean sea levels will be rising, what we can do is split the atom of or the molecule of water, get the oxygen free, so we have more oxygen in the air, release the hydrogen, it'll go into outer space and fly away, so we don't have to worry about the hydrogen.
Right, yeah, the Earth is a cup that's constantly filling up with hydrogen because the sun's constantly like a big spigot full of hydrogen hitting us. And helium. Unfortunately, the helium's not able to bond with anything, so it can get trapped and hang around. So it just gets blown away with the solar wind when it's too high over the lip of the gravity well.
But the way I understand it is that if you release a bunch of hydrogen into the atmosphere right now, it will mostly just end up in outer space. It's not
right. It's the lightest element. Yeah, it eventually ends up so far above the atmosphere, it doesn't drift away on its own. We're being bombarded, even with our magnetosphere. The sun is pelting the crap out of the surface of the atmosphere. So those solar winds blow away any helium that you basically release from the Earth. You put it in a balloon or something like that, it's gone forever. Because once that gets to the upper atmosphere, the sun will just blow it right away.
Right.
And it won't come back.
So literally,
and we use those for MRIs
system
and whatnot. So we need to find out how to make more helium, like with cold fusion or something like that. Even if it's not generating power, if we can turn hydrogen into helium so it can be used for medical equipment, that thing will be worth way more than its weight in, iridium. Screw platinum and gold. Most precious element on this, or most the rarest element on the planet is iridium. So it'd be worth more than a solid chunk of iridium.
Helium is a real problem because it does come from mining natural gas. And
helium?
It's a finite resource on the planet, but it's extremely abundant in outer space.
Oh, yeah. Yeah, if we could put something out there to catch it and then send it down in tanks or something, the sun's pumping out tons of it.
Yeah, there's no shortage of helium. Helium was actually one of the later elements that was discovered. It was discovered through a space telescope using a spectrometer.
They managed to get it down to a liquid state too, because it's like a fraction of a degree of absolute zero.
And Jeremy pointed this out to me the other day. It is also the smallest atom as well, because the atoms get smaller. On the right side of the chart, on the left side of the chart, they're large, and then on the right side, they get smaller. So helium is all the way on the right top corner, so it's the smallest element, smaller than hydrogen, actually.
I wonder if that's because there's more force pulling on the electrons, so the shell is smaller than it is on the hydrogen, with it having 2 protons instead of just 1.
It's very difficult to contain hydrogen, helium in liquid form. They needed special materials.
It's difficult to contain, period. That stuff goes right through a solid steel plate. It just worms its way in between the atoms of iron. So
yeah, that's why
graphene's a solution. There's a deal where they were checking and they found that water molecules cause the pores in the graphene, the hexagonal rings, to relax. So water will go through the membrane. But helium, it's acting like when you touch dry a sponge up, it causes it to shrink, and it blocks the helium from going through. It's the only thing I know of that we could probably use for retaining helium indefinitely. Because every time the helium tries to escape by touching the graphene membrane, it'll shrink up and block it. So there's a lot of interesting stuff with graphene that I think they're overblowing the things that they want from it and totally missing the things that it could provide, like being able to dope one side with the correct carbon atoms in it, with hydrogen, you can make a very strong magnetic structure that's natural because of its structure. So, it's not going to degrade unless the atoms themselves have degraded and, turned into something else, like hydrogen eventually becoming helium or something, headed toward that iron, that iron hole that's basically everything's headed towards. So.
Wow. Yeah, there's a lot going on with helium, and it's also a superfluid, which is, I think it's the only material that we know of that is a superfluid, has zero viscosity, and if you had a cup of helium, the surface tension on the side will continuously push the helium upwards against the force of gravity until it comes over the edge of the cup, and then it starts pulling itself down and it'll just go over the edges of the cup. And of course, it's only liquid at either high pressures or extremely low temperatures, or combination of both. So
I wonder if its negative charge from the electrons creates too strong of an exterior negative force for the protons that are in other elements, in order to basically try to latch onto that negative charge to pull it toward it. That would be almost like having an anti-gravity device, because it would instantly repel itself away from any matter and keep repelling it away. If you could push enough distance between the protons and all of the electrons, like in a plasma state, push them all to the outside of the shell. If you can control which side it's doing that on too, then you could control what direction your flow is. But then you run the risk of, like, say, when you take a magnet and you block one side, if you push that side up against like a piece of steel and let go, it'll flip over, so the magnet will stick to the piece of steel. So I would imagine if you're too close to a planet and you only have one side, pushing away, it would cause it to flip over and then be pulled back down. Just because you don't have the distance between your protons and electrons in order to basically shield the attraction. So. Right.
Sean, are you there? I see you're. You haven't chimed in yet. Sean, can you hear me?
He hasn't said anything on Skype in a while either.
Yeah, he's been a little quiet. This has been going on.
There we go. There it is.
Oh.
Yeah, I'm on. Yeah, I've been listening.
Okay, how's everything, Sean? We haven't spoken to you in a while.
Oh yeah, doing well. Just keeping it around.
What you been up to? Is there anything new in the papers and the research?
Not much really. No, just Mirabeau, and this book is ridiculously expensive now. That's about it.
Oh, so you're reading some ridiculously expensive book?
Yeah, now it is ridiculously expensive. It wasn't like a month ago.
Okay.
Yeah.
That piques my interest. What's the topic of conversation in the book?
It's Lake Mirabeau's book. Shoot, what is it called? It's called Lightcraft, Flight Manual, Tech Manual.
Oh, Lightcraft.
Yeah, Tech Manual. I can't find. It was selling for like $60, and now it's like $1,000 some odd dollars.
What's it talking about?
Just the magnetohydrodynamic craft, the ionic propulsion, magnetic levitational belts that a person could wear so they could suck you into the craft. A lot of cool stuff. They have oh man, too much to cover, really.
Is there anything like new and exciting in there, or is it all just regurgitated?
No, it's actually fairly exciting. I think when it comes, it's I don't know how to explain it exactly. NASA did a bunch of work on all this stuff, and they had a bunch of books and documents on it all, and he just pretty much made a book out of it. And he ran Rensselaer Polytech Institute in Troy, New York. And he had his own school there that he was teaching this technology to. It was using magnetic lasers, or sorry, microwave beam technology and laser beam technology in order to create this propulsion system. And he'd hit the craft with it, and it'd excite the molecules around it, and he'd create a plasma and use magnetohydrodynamics in order to manipulate the plasma in order to launch the vehicle. He also used ion propulsion in order to lift it and travel at slow speeds before they hit it with the magnetic beams, or see the microwave beam, and launch the vehicle. It's pretty wild.
So I think I saw a video of that. There was like a donut-shaped aluminum device that they were pumping with really powerful laser pulses, and there was like this popping sound every time they got the laser to fire, and it'll go pop, 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 and sort of fly up.
Yeah, that's it. Yeah, that was the prototype and proof of concept, and then he ended up making bigger ones, and they launched those, and then the Space Command came in and said, "Thank you. Don't talk about it."
Oh.
You know.
Why does that happen? No conspiracy going on here, right?
Yeah. Just one of those.
Yeah, this is all, business as usual. Everyone's being open source and, honest, of course. But, yeah. Actually, at the previous APEC, not this last one, we had the whole trifecta. We had Space Force, there was SpaceX. These are unofficial channels. There was also some Pentagon officials there as well. And Lockheed Martin, at least it was a username, and he preferred to call himself Martin, showed up at APEC.
Sorry, they had the tags with the names of these companies.
At APEC, yeah.
Really?
Yeah.
And
I
don't know.
Tim
what
reached
to think
out.
of
Those
that.
are real people. Those are people who actually work at those companies that are interested in what we're doing.
Because we didn't have the right people on for them to see. Really, like
I was on, and I gave that presentation. I was hoping Jeremiah would be on after me, but he wasn't ready.
Well, what I'm saying is, like, we didn't have Ben Durick, we didn't have, all the real meat and potatoes. That
I know. It's hard to time everything, and what really sucked is that we had that Paul Murad thing on first, but they didn't chime in for that. They were there they came in at the last few minutes of him, and were really there to see my presentation and Jeremiah's. That presentation with Paul Murad really had me pissed off, just like Jeremy Riss was also pissed about that. I tried setting up a pre-conference conversation with Paul, and he didn't show up to that. Just, to go over what he was going to talk about. We need to clean up our act with the kind of people that we're bringing on and the kind of things they're talking about, because we don't want to be, that fringe where, here's some aliens. That's Mike and Paul. I don't know what this is.
Bill and Ted.
No, that's Bill and Ted. Like, okay. I mean, Paul Murad does have a lot of credibility from all the stuff that he's done, and he has credibility to throw away, and he doesn't give a shit anymore, but we don't. So go figure. But Paul LaViolette, he's one of the heroes of this field, but he throws everyone under the bus, with his first 10 minutes. He's like, here's modern science. It's all the garbage. We're not going to pay any attention to that. It's all wrong. I don't like anyone who says all wrong, because there's nothing that's all wrong, and there's almost nothing that's all right either. It's mostly always somewhere in the middle. It could sway in either way. Dejan, you hear me on this. There's nothing that's perfect right or perfect wrong.
I don't. It's not like that at all, because. As they say, we are not limited by our imagination. We are limited by, laws of nature or physics. Physics constrains us in what is possible, and things which are possible are very repeatable in a sense they always contain these laws of nature. So, and then question is how imperfect is something. If something is one part in million imperfect and 99.99999 right, what's imperfection? General relativity is accurate to one part in 10,000. You couldn't really say, oh yes, but one part in a million is inaccurate. How well? For all the practical purposes, we could predict behavior of universe. We could design a GPS craft. That's all done from general relativity. So
right. But you also need to consider the fact that you need to break general relativity down to the parts that we know are correct, to the parts that we assume are correct because we're attaching it to the same theory. So yeah, there are certain things that are binary. Yes or no. Gravity does pull. We've never seen it push, or push things away. So there are things that are binary our understanding of the universe says this is how it works. And there's also things that come to the issue of calibration, of how accurate is our test measurements. It could be that we only got to 99.9 or 1 in 10,000 because that's what our equipment can test. So
it could also be that there's some other factor we don't know about that by studying that thing that's wrong, you could find that missing component.
That is true, and that's
be wrong, and then you can complete the rest of the formula.
Exactly. That's what Einstein did, because he was taking Newton's formula of gravity and he modified it based on the work of astronomers who were looking at the perihelion of the orbit of Mercury and how it changed, and how Newton's physics didn't take that into effect, and then there was some math that was written up for it. And Einstein was able to incorporate that all together. He was working on the backs of other scientists who did all that research, so it wasn't stuff that just came up on his own, and he was helped by others, but he put the pieces together and was able to get the math that explained the perihelion of the
Mercury.
The orbit of Mercury. And by doing that, he proved, at least a mathematic component of his theory. And that was one of the big things that he added, getting it a little bit more accurate. But those numbers only matter when you have really strong gravitational fields close to each other. Then the numbers get a little tighter, and extra things start to happen. But
I want to know why they switched from a measurement device that was using atoms for the measurement for time and switched to something that uses light. Because I seem to recall there was some discussion about how their measurements for light had been accurate for a while, and then when they went back to re-examine it, like at a college or something for one of their what do you call it? They're basically their studies. It was basically just a workbook thing that you had to go through and do the same thing, so you knew how to use the equipment and whatnot. And they found that the measurement for the speed of light had changed. There was something wrong with it. And after further testing, they were saying that the speed of light had actually altered, which gave me the idea that maybe the speed isn't changed. It's the size of everything has changed, because we're going through like a pulsation effect, where sometimes we're this wide, sometimes we're this wide, depending on the frequency and whatnot that the whole universe is resting on. That could have explained everything if we would have looked at it in that manner, instead of just setting light as the measurement to measure time by. That way, if it's going slower, our time slows down. If it's going faster, our time speeds up, meaning our measurement of time.
Exactly.
That's
a problem that I have.
Time flow itself.
That's a problem that we have with many statements that are made in science. You got to really dive into the details of how did they make that measurement? What are they using as their constants? And if you want to explore the fringes of science, really, you got to get down to that nitty-gritty level. did they use a mirror? What was the mirror made out of? What kind of light? Why were they using light instead of that? All of these things are considerations when you're trying to figure out, the fringes of science. Because if you're assuming that light is a constant, which we know it's not, then and using that constant to measure time, well, we know space and time are connected. So how is that a constant? Like,
maybe the speed of light is a constant because that's just the amount of energy it takes for it to reach the point of going from an electron to being a photon. But if you can inject more energy into it than it takes to basically produce that excitation without it being turned into frequental vibration on that electron, you could end up with those particles moving faster than light.
Very good, very good. Tim Ventura actually simplified this for me. I really like his explanation. You look at Dejan's glasses; they curve light. So, according to some theories, they are warp drives because they're curving light, right? Warp drive, yeah. Okay, so he was explaining to me that actually it's not the speed of light that's changing; it's the transition. The light, as it's traveling through the glass, is transitioning from photon to electron. That is where the time delay happens. That's why the thicker glass, curves and slows it down.
Right. It's acting as a wave passing through the material because the particle's been absorbed, and it's not the same particle most likely coming out the other side.
Yeah, it's been
like
transitioned many times.
Newman's cradle, where basically smack the end of the row and out the other side it pops. The thing that I've been looking at for my 3D printing is a mechanism of control is that you have three effects that light has on material. It can either be absorbed by it, and it either causes an excitation where you get an electron released as another photon, sometimes at a different frequency, or it forms thermal energy, meaning it causes the whole thing to vibrate, and it raises the energy state of the electrons during that time because it adds more energy to them so that they expand their as long as you have enough energy, they expand their valence level. So you could cause a stronger negative charge because it's further from the protons in the core of the atom. You also have reflection where it's bouncing off of it, right? And when something is reflecting off it, there's a possibility that when it reflects off it, it's going to actually take energy from it when it collides with it. Just have to pick the right frequency, and you should be able to basically lower the electron value and force the electrons lower by taking some of their energy, cause their valence level to fall, so you can cause one of those electrons to fall into one of the lower shells. Now you have a positive charge that's poking through the electron shells because of the proton energy reaching as far as it is. Normally it's shielded by the electron layer at the right height, but once you dip below that, like a magnetic field, if you go too deep inside of it with something that's not able to completely absorb it, it's just basically creating a barrier so you can't get to it. Well, now you can get to the positive charge to get something that is negatively charged to bond to it. That way you can get things to bond where you want them using the light, and you push everything with an electrostatic charge like capacitor plates that you set up inside of like water to pull the hydrogen one way and the oxygen the other way. You can use the same process to basically give it almost the amount of energy it needs for those particles of those elements to bond, but not enough. And it requires the light to give it the last extra boost to get it to fully give it the energy to make the atomic bond or the molecular bond. That way you can then use that to control where everything's being built and not have to worry about, I've got to do with this one and I've got to do this one. 3D printers now, fused filament. Why do they take so long? It's because you have a tiny little nozzle to get the resolution you want that has to travel over the entire surface of the object, every single layer. Hundreds of miles of movement before a single print that's only 3 inches tall can be finished. If we had a sweeper where you have a slit that the filament is coming out of, and then have square rods of steel to push down in or pull back out of that slit in any arrangement that are, you could have like 1,000 of them in a row that you could then open or close any opening of the nozzle along that row. So if you need to do a solid
that's like
area,
a dot
you can pull
printer.
back in 1,000 layers whoosh, all at once.
That's like
right.
a dot, like a dot printer.
Right, like a dot matrix. In fact, that was where I got the idea. And the idea is to go from the round dot to using square rods, so that way you can just fill the whole thing up. Then it has to rotate, though, because if you're wanting to lay down a smooth line around in a circle and you're doing two lines, well, you're opening two nozzles next to each other. Now you have to rotate them so that they're staying, so that they're lined up with the center of the circle as they go around. So, it's going to be some tricks, like basically putting together what are they, the microchip that they have inside of WS2812B LEDs, the RGB LEDs, that they have a little circuit so you can just send data to it, and it'll use the voltage you send to it to give the right amount of rate of pulsation to the red, the green, the blue to get different colors. So I need something like that I can run from, a 3D printer, where I can send a code to it with the G code that tells a whole row of these little chips which of those solenoids to pull up or push down, instead of it having to be every single one of them has to have their own contact. Just send a data stream along one wire and then have a return. That way you can just put brushes for the first generation and later build some graphite like bearings or something that roll around on it, so that way basically there's no degradation from the electrical charge passing through the material for the bearings, but you've got non-wear rotation on like metal tracks that are attached to the head that basically provide the data, the positive and the negative source, so that way you can run your heater for the whole thing. You can run all the power whenever the solenoids are needing power to push down or pull back. And
I'm thinking this whole thing up in my head right now, just trying to imagine how the solenoids would be placed.
Right. They'll have to be pretty small, and you have to stair step them, so that way basically the wire can basically pass right beside the solenoid of the next one to get to the solenoid. So it's not, its center's basically half over and whatnot to get enough of them in there.
And you're going to have to use
together.
High temp materials are capped on for everything, because everything's going to get hot there in the head.
Actually, my plan has always been to go to a copper core with a titanium exterior, because titanium has a low thermal conductivity, so it'll trap the heat that's produced by the heater inside of the copper core to keep it going to the filament, and then a titanium neck for the whole thing, so that way it's going to have less thermal conductivity to get through the neck, and then the break where you screw the two pieces together, a piece of aerogel, just a ring of aerogel, to try to block that heat as much as possible from going up into it. That way the filament as it's going down through isn't getting hot before it gets in there, and then it gums up the works for the rotation mechanism. So, and then that whole head has got to be its own mechanism, where basically I'm going to have to make the whole stepper motor mechanism for that, so that it's basically the nozzle and the head and the neck and everything form the motor.
Tom, can you tilt your camera so we can see what you're describing with your hand?
Oh,
yeah.
Well, yeah. So like I said, though, that way you can force the filament straight. Like imagine your motor, with the motor being that part of the head, and the spindle of the motor is basically the hole the filament's going through to get to all the heating mechanisms and whatnot out the back side of the motor. So, and then again, using those brushes so you can control those four wires for the motor. I'll have to do some work on basically some of the stuff I'm planning for printing magnetic material and whatnot, so I can get the resolution I need. Because if you're doing like a very large circle and you only have 200 increments that you're dividing by, say, 8 safely, you can divide it by 16 and 32, but those increments of division are never accurate every single time, like they are with the lower resolution of division. So you're going to end up with basically a bunch of stair steps forming, and it's not going to be a perfect round circle. Whereas if you can divide that up by, say, 2,000 or 3,000 steps, you're going to get a lot more resolution out of it. So that way you can go bigger without it getting jagged looking, not pixelated, but vectored, without it getting vector looking. So
okay, but would
it's definitely a challenge. So
this would just speed up the printing process. It wouldn't give us any new capabilities, right?
No, right. Because the idea is to basically get rid of, like, I want the plastic part to be on the order of basically being able to compete with injection molding. That way there's plenty of time left over for slowing down for things like printing out the actual, the layers for like semiconductor dopants that you're forming on like a wafer to basically print a CPU, or you're printing RAM, or you're, laying down the material over top of that to protect it and whatnot and move on to the next layer of your circuit, or you're going through and laying down a layer of circuit board and then a layer of traces and then a layer of circuit board material and, alternating so you can get 7, 8, 9, 10 layered circuit boards, with traces inside, so that way you can get your wiring without anything being external and then, wasting energy and all the other reasons that they have for basically embedding traces of metal inside the layers of like a sandwich. So, but all of that stuff's going to take time, and the more control on precision you need, the longer it's going to take, even if you're using the same level of being able to put out the same amount of incremental components all at once. They're going to have to be smaller and tighter. But how much material is there in a CPU in your cell phone? So if you have to slow that down to say 10 times what it takes to print the case, but the case literally prints out in 7.8 seconds, then that means that the amount of time it's going to take for the CPU is well within the range of being able to print a new phone out of an old phone you broke down in the thing and shuffled all the stuff away and sorted it so you can use it to print the new phone. And you're not waiting 6 months or a year or 10 years just to print one cell phone because of how long it would take with what we're using now. If we were using that same level of technology with the new materials to print semiconductor layers without masks, you're using digital masks rather than using physical masks. So, like we use now.
All right.
So.
The current level of technology that it takes to print these circuit boards, from my understanding, is clean room level, up to the
Right.
wazoo. And everyone's wearing hair masks, and they got these HEPA filters and all that stuff.
That's because they're working with stuff that when it's actually being created, it's inside of a vacuum. That we have not left the vacuum tube era. The vacuum tube era we're still in it, but it has given us this extra step of the solid state era because all the solid state stuff is made in the vacuum tubes now. They're not little vacuum tubes that you put inside of electronic device that you're, amplifying your guitar with. No, they're giant vacuum tubes that all this stuff is inside of. And then you've got the elements and whatnot are actually causing materials to vaporize and stick to the surface to build your layers up and whatnot. And they have to keep taking it out of the tank. That means devacuuming, remove the mask, put a new mask on, or actually, no, it's remove the mask after the etching is done, and then they put a new mask on after they put the next layer on. They got to put the new mask on by pulling it out again and put it through the etching process and then put it back in and start all over again for each and every single layer. So a truly three-dimensional CPU isn't really possible feasibly. Like, we could do it, but it would take so long that one CPU would be like $10 million. So we're stuck with this two-dimensional architecture that has limited the ability of processing we can do, where we're having to jam massive amounts of speed at it to use the small amount of material that we've been able to produce in order to get any kind of useful computations out of it. If we had 1,000 or 2,000 layers of CPUs built on top of each other, you wouldn't have to worry about the heat buildup because you could run all that much slower and just divide up all of your computation among the system, use parallel processing in it. So you could literally have a Cray supercomputer in a little cube, So today's modern Cray supercomputer, where they're using the Tesla GPUs and whatnot, and they've got whole racks, in rooms filled up with them. They just fit it all in a little cube, And this is something that could give us that too, so that we could have a thicker CPU that has a lot more computational power stacked on top of itself with three-dimensional architecture to communicate below and above through the layers. You get a lot more work than just communicating, in a flat grid, because you're missing the up and down action that you basically be poking and prodding to put, data from here to there and, grabbing algorithms, algorithm data from it.
So what you are saying, you are talking about having 3D processors.
Right.
Wow, that's phenomenal, because they are talking now that we are completely stuck with the production of new processors, because these transistors became so small. They are only a few atoms wide. So there is no more room for improving the speed by reducing the size of transistors inside the CPU.
Too much electron leakage. They bore through and pop out the other side, and then you get dirt. Dirty data. So that's what I want. One of those quantum computer chips.
You are completely
they have
right.
that problem. Let it have that, because I want to poke data in it and let the background noise that forms on it have it poke back in there and look at that data and see what new stuff it comes up with that the computer would never been able to calculate out and get to any of those data sets that it's getting now from that random background information. It's almost like giving a computer an imagination.
But the only problem is, if you stack them on top of each other, you are going to increase the amount of heat.
Right, that's why you run slower, so that way you don't have to worry about that. And your architecture. If you have thicker traces of architecture that is better at thermal conductivity, like using silver. Silver's got an extremely high thermal conductivity, just like it has a higher electrical conductivity than copper. If you got enough of that material that's coming out the edges, you could have heat sinking from all around it, pulling the heat out too. So, I mean, there's going to be challenges no matter where you go. Just like one of the processors I'm trying to, I'm still working on some of the math and the modeling and whatnot for it, but it basically uses alkaline and acidic gases to push them in and out of areas in the transistor arrays so that you can change the transistor's state. And the transistor is entirely made out of carbon nanotubes. So that way, when it's sticking to the inside of the nanotubes, it's basically altering the balanced nature of the carbon atom. So now it's either positively charged or negatively charged. So you can not only swap back and forth between an NPN and a PNP transistor, but you could actually have several states. That way you could have a -3, -2, -1, your zero state, which is just basically a resistor. Instead of being completely off, it's the reverse. And then have a positive 1, 2, and 3 to work with. So you're basically pulling, requiring more electrical charge in order to basically even poke through the barrier you've created, so that you can then basically consider that a reduction of the basically true division and subtraction, instead of using tricks where everything's all multiplication and addition, but then you use mathematical tricks to simulate subtraction and division in a standard CPU now. So by just using your on and off gates. So that might be the only way we can actually get to a point where we could do more AI-like work, if we really want to experiment with that and take the chance on that. It takes a lot to basically simulate a brain, because we have an awful lot going on inside a single neuron. So it's got to be another way to basically make those gates more dynamic than what they already are. And I remember ages ago people talking about, what was it, the trans capacitor? Have you ever heard of that term?
A trans capacitor.
Right. You got your resistors that they've made transistors off of the diode concept, because the diode is basically a resistor check valve. So there's resistance, but if you go the wrong direction, it slams the valve shut. Right? So the trans capacitor would have to have something to do with basically using capacitance to, I'm guessing, to affect the flow the same way that the transistor is enabling it to open and close it, because that is kind of a trans capacitor already. The third leg is basically a connection to a doped capacitive plate that has a bias. So when you reverse the bias by force, it opens it up then,
Talking about capacitors, Nam just messaged me that he has some asymmetric capacitors that he's working on, similar to the Nazi bell. Inconclusive results. He's going to get the capacitors right now that he's working on. I think he's there in a construction lab, something like that. He'll pull it up. He'll show us on the screen what exactly it is he's working on. We're doing lots of asymmetric capacitor work right now. Mostly it's Jeremiah and Wayne that are doing that. Waiting for, I got some parts over here that are going to go into a press, allowing us to compress the CCTO, their calcium copper titanate oxide, into really fine discs or compressed discs that will then be able to maximize the dielectric constant. K value of 200,000 is advertised with the material. So if we can get a capacitor or parallel plate capacitor with that kind of capacitance in such a small space, who knows? We might see something. Nam, what do you got?
What material are you guys using?
CCTO. That's what we have here in the lab. But Nam might have something else. Nam, what do you got?
Yeah.
I have two things to show you. First, the capacitor is simple like this. You see it?
Yep.
It has a positive plates in a circle under the resin, and this is the negative electrode. When it is in this configuration, a force we will push it forward. It's just that simple.
And you could change the capacitance by moving that ring back and forth. With it not being attached, that means like if you pull it away, it increases what the voltage value.
Yes, when you change the position of the electrode, the thrust will change.
Nam, can you pick it up? We see your face. We don't see the capacitor, though. It's below the camera.
Oh.
Oh, yeah, there. Now we can see it.
You see it?
Yeah, we see it good now.
Yeah.
A plate over and a hopper under. It's just that simple.
Wow. Just to give everyone a heads up of who Nam Tran is, he's a big hero of mine. Found him on Facebook. He's been working on this independently for quite some time. Nam, how long have you been doing anti-gravity research for?
I have been doing this. I have been done this since 2015.
2015.
It has been 6 years.
6 years, and you work for Vietnam Airlines, making parts for the airplanes in a manufacturing lab. I understand. You're one of the.
No, I don't make parts. I just fix parts. I fix I fix the whole aircraft. But I don't want to talk much about my job because it's just for the money, and my attention now is anti-gravity.
Amen. Amen. That's what it's all about.
I'll definitely back to that. Absolutely. Yep. Same here. You just got to do what you got to do to get by. But ultimately, what we're doing could potentially revolutionize technology and save the species from its own demise.
Yeah, I know that.
So whether you're repairing aircraft or making leather masks.
I know that aviation will someday die, and only anti-gravity can save us.
Absolutely. We need something to get off of this dirt ball, and something that allows us to do it without burning the resources that we have here.
Now, do you like to see my energy belt? Although it's not successful, you still want to see it?
Yes, we love unsuccessful experiments. It's fail-forward research. That's Wayne Ojala's channel, and that's literally what we're doing. We're showing off this didn't work in this exact configuration, and getting into
hopefully gathering all the data too, so that way you know what it did do.
Exactly. And I'm gonna show off Nam's video right now. Nam, you are spotlighted. Just make sure to keep the sample right in the camera view so we can see it. There you go. Okay, what is that?
Yeah, this is the model of the energy belt. It has two discs. One above the other, and these rotate in two directions.
Are they counter rotating? They're spinning.
What's that?
They're spinning in opposite directions.
Yes, it is. They are rotating in opposite directions. You can see the upper disc, and below it there's another disc, and it's counter rotating.
Man, that is very cool. That is very, very cool.
It's a very nice experiment.
Is that the
Yes,
same
it is.
white material that everybody else is using to build all those frames with? 'Cause I'm wondering what that stuff is. Is that builder's
That's a
board or
3D
something?
print.
Oh, is it 3D printed? Oh, okay.
Um,
ABS or PLA? Or is it like a high temperature like nylon or something?
The frame is 3D printed, and the disc is from the CNC.
Yeah, NAM specializes in making really nice looking replications of these experiments. And as he specified earlier, he doesn't do all of the manufacturing on it. He has some of his buddies do it, which is wonderful. Getting everyone
That's
together,
always good to have help, yeah.
especially when you have.
Let me finish my
Go ahead.
model. I have a white here, and a big hub around. I find high voltage between the center shaft and the outer hub. It's about 26 kV, 26 kilovolts. And when I put the whole device on my digital balance, digital scale, it shows about 2.5 gram loss of weight. And I think it's not a solid proof. But when I stop the spinning and only apply voltage, the weight doesn't change. It only changes when the discs are rotating. The two discs are counter rotating.
Did you do a
noise
negative
is
test
more.
with just the spinning?
Yes, the way only changes when the discs are rotating, and the loss is 0.5 gram.
Okay, so we're definitely seeing like a 2 gram weight difference between when it's just spinning or when it's spinning with the high voltage. So something
Yes.
the combination is definitely doing something there. What is your noise level in the scale? What's the noise floor?
You are right. That's my concern. I think the results could be the noise, and I don't trust the outcome of this experiment.
Both of the discs are aluminum, right?
Yes, the discs are aluminum.
Okay, so they're both paramagnetic.
Which
I'm wondering if you altered those discs to make stacks of aluminum, steel, and bismuth in a series of like you do aluminum, steel, bismuth, steel, aluminum. Two layers of aluminum and then another, go back to through the series. Kind of I'm just thinking like maybe the orientation of the material and its effect that it has on the material itself, because of the type of material, might have some effect on helping improve the thrust that you're looking for. Making sure they're all completely connected because each of them has their own conductivity too. So they have a different rate of conductivity, which I would look at it as like a different speed of conductivity, so you can shape the flow of energy through it by using different materials in that stacking system.
Are you talking about the electron drift velocity of various materials?
Well, okay. You know that the conductivity of what the conductivity of steel is, and you
Yeah, it's
know how
pretty
much
low, but it has
lower.
a very, very high quantity of mobile electrons.
Right, and then aluminum has a much higher conductivity. Bismuth is the lowest conductivity of those three,
But
but
also
like
has
you said, it
the
has even
highest
more
electron
electrons.
mobility.
Right. So that's what I'm thinking is like if the stacking were done, like bonding them together though, not like putting an insulator between them. You want free electron flow throughout all of the layers. So
That's a really
I
interesting
understand,
point. No, I was thinking the same thing.
I see what you're saying, but back in the day, they say that they used mercury, and more specifically, red mercury for the position of this.
you're talking about from the bell?
Yes,
Okay.
they're not using bismuth or iron, but red mercury.
Right.
What is red
I
mercury?
don't put too much stock in their effectiveness at what they were doing. Like I know that they understood some really key components to how things work, but they still had this mentality of like driving 1,000 slaves into the Antarctic to get an ice cube for Hitler. You know what I mean? It's like we can do it much more efficiently than that and get the same effect out of if we figure out why the stuff works the way it does and then use better materials because of its arrangement. Now, like alone, it may not work better. It may work much worse. Like if you're just using solid aluminum instead of a solid pool of mercury, you may not get anywhere near the effect. But whenever you start using the peculiar interfacing that you get between different materials, you might be able to get a better effect than even the mercury had, and not have to worry about any chance of spillage or anything like that. Because when it's spinning, it's going to want to push out, out of the container and whatnot. So I think that would probably affect your electron mobility too if the atoms are able to freely move around within the medium too. Which, I mean, maybe that'd be beneficial, but then again, it might be a detriment that if you could control that and not allow it to move around, like using a standing wave magnetic field on the atoms that are actually in the mercury, so you can control what direction and movement that the material is moving from inside to out, not just from rotation, so that it can't just push out all the way to the edge,
We were.
Are you guys familiar with the origin?
One sec. I just wanted to touch on the mercury thing. We'll get to the RGM in a second. Jeremiah actually sent me over a patent that we were going over. It got me super excited about spinning mercury, and just to simplify it.
Mark and I have been talking about, to kind of preface on the story while he finds the patent. We have been talking about this particular way to move mercury, where it moved faster in one direction than the other, or basically the pathway, the momentum that was in the upwards mercury stream and the momentum that was in the downwards mercury stream, because there was much less mass in the upwards mercury stream, it had consequently higher momentum. So the areas of the entire engine or of the drive where the momentum is high is always on one side and it's low on the other. So effectively, this thing plans to produce a force as a result. And then we just came across this convenient patent, which pretty much shows you exactly one guy's idea of how you can do it.
And I am pulling it up right now, just downloading hydrodynamic inertial impulse propulsion, and open it up. And let me share screen. There we go. Share screen. Now I am sharing, and let me just make sure that everything is working here. So I got so much going on. Can you guys hear me?
Mm-hmm.
Okay. Can you see the patent?
Mm-hmm.
Yes, we can see.
Okay, hold on one second. Where is the Zoom call?
The drawing almost looks like the cross-section Isaac Arthur was showing for orbital rings, with the high-speed wire being propelled around it to create a centrifugal force to keep it from collapsing on the planet. That way you could keep them really close to the Earth. And the ring itself, the outside you're walking around, is stable. It's not rotating around the Earth.
There's a little problem showing this on the live stream. Let me just try to fix that a second. We ended up with just a frozen picture. Yeah, we are still alive. Okay,
I had
so
it shrunk down to 50% too, so I had to expand it.
okay, so basically, whereas it gets to the meat and potatoes right over here. Basically, what we're looking at is a instead of spinning Mercury around in a circle, we're going to spin it in just a half circle. Now, let's think of that for a second. When you're spinning Mercury or spinning anything in a circle, if you take a weight on the end of a string and spin it around, there's no linear momentum created because all the forces equalize, right? But what happens if you have the ability, or you're flowing a heavy material such as water or mercury, which is more dense, in the shape of a D? So you get all of that angular momentum going on half a circle, pushing it in one direction, and then there's no force canceling it out because it just takes the shortcut across. You only have half the circle.
So if you had a bunch of cat hair going through that thing against a bunch of, say, nylon, that flat surface is where all the majority of your electrostatic energy would build up, instead of the other area where it's got a cleaner, smoother flow, where it's not making as hard a contact on it. So I'm wondering what the mercury would do when it's making contact with that surface, with the electron exchange between the atoms and the surface.
It's just something to think about, and we really want to try that. What do you guys think of that idea?
Seems like if it's legitimate, that point where it's making that sharp turn is probably where you're looking for the most effect that you're getting in the other secondary, like, sharp turn.
If you do integration over that whole path, what you will get that it doesn't really matter whether path is whether he is taking a shortcut or going around the circle. When you do integration, these two things will always be the same. So he is not achieving anything with taking that shortcut.
Well, with the slamming into that corner as it's turning, wouldn't that mean that if that has any effect, couldn't you just add something to the circle so that you could intermittently push it in from different angles to get whatever energy it is coming off it in any direction then?
Momentum in the shortcut would be exactly the same as momentum in the curved path. That comes from a simple integration.
Right, you're just looking at more centrifugal force slamming into that because it's forcing it to turn faster.
Yeah,
but that's what I was thinking, is the atom only has so much energy to hold all the components together, and when you slam it into something like that, you get more potential out of it. Like I said, like if you put two plates together, this is what I've been working with.
What if we did this?
Stuff.
What if we had a really thick
but one thing,
if the flat part was really thick, like made it a 1-inch diameter, and then the half circle was a 1/4-inch diameter, so it was, the mercury would have to speed up around that edge. Wouldn't you end up with a nonlinear force?
You would get centrifugal force on the curved part. That's on a flat part, you will get no centrifugal force.
Right. So if we have centrifugal force just on one side, wouldn't it move toward the centrifugal force? Or does the edges count?
Hold on. How many magnetic, mercury-based pieces of tech have you guys built so far?
Not many.
Okay,
we dabbled with it.
This may sound stupid, but I got to ask anyway. You know why they won't let you take mercury on a plane?
Very dangerous.
Well, absolutely, if anything gets out, it'll eat through the freaking plane and turn it into an amalgam.
Right. Okay. I was just wondering what you guys are using to put the mercury in. So a lot of people miss this. They don't realize mercury will dissolve other metals depending on the type of metal.
Borosilicate or stainless. It's the only two viable options.
Why not plastic?
Or plastic.
Good.
There is this metal called gadolinium, which if you hold it in your hand, it will melt.
Right.
So all the experiments that you could do with mercury, you could do with gadolinium, but you have no danger of poisoning yourself. and you could buy it on eBay. I don't know, if you want a large quantity, maybe a liter of it or 2 pints, that costs about $500. I've seen it on eBay.
Doesn't that have like a really low temperature transition too, from being ferromagnetic and being either paramagnetic or diamagnetic?
I don't know.
Meaning it's very easy to switch back and forth between that. Like you can just literally use heat and magnets to basically make a wheel spin because of the temperature you're changing the gadolinium back in. I thought that was the element. It might be something else, but.
Well, it could be checked on what's called Wikipedia quickly.
Yeah.
That's something to use instead of mercury. And, you know, you could do lots of interesting experiments with the liquid metals. It's a completely unique material.
And getting the mercury is not that hard either. So that way, if you find something relevant and you think that there's more potential with the mercury, then you could take the chance with the more dangerous material after you verify with the gadolinium. Maybe take a little extra time too to make sure everything is sealed, so you don't have to worry about it getting out.
But
No
problem,
glass.
but problem with both gadolinium and mercury is that they eat into other metals.
Right,
So,
form amalgams.
yeah, they form amalgams and they dissolve them basically.
Right. That's what I thought was so funny. If you spill a little thing of mercury, it basically will destroy the hull of the plane because they're made out of titanium and aluminum.
Yeah, there is a video on YouTube where a guy poured mercury on an aluminum bar, and it just kind of like chemically transformed into some compound and drilled a big hole into aluminum.
And
Even steel will be kind of dented, and
it's hard to believe they used to use that to separate all the gold out of something when it was difficult to get it out. Instead of using heat, they just dissolved it out with the mercury and then boil the mercury off, leaving traces of it, of course, in the gold, so that way people are getting sick off it, not knowing it.
Peter Middleton wrote, what you really want to do is propel mercury in one direction at extremely high velocity, and then pump it back at low velocity in a recycling directional inertial drive system. Why would that work?
That's correct. Yeah, he's got it right. That's exactly right. You want a difference in the velocity and consequent difference in the inertia because
the pressure.
Right, because the idea is that the equations for conservation momentum don't apply linearly across a scalar domain. In fact, actually contain a missing variable. So that's what that system attempts to capitalize on, is if that variable is in fact missing, and that there is a nonlinear response between two independent frames of reference of a fluid flowing at two different parts of that system, then there could be a force there. But it says the same thing about electricity too, that all forces should ultimately equal zero, because if you take a look at the Heaviside Maxwell force, right, all current flows in closed loops, and only closed loops are tolerated. So magnetic systems or electrical systems that are open loops, they aren't really tolerated, and everything is assumed to be zero, but it isn't necessarily that way. That's what those 4 patents are about with with Douglas Torr and Nisicus and Bates and Brown. Those 4 sets of patents by those 4 inventors all talk about this nonlinearity that's not included in general relativity. So
That's interesting. I actually had a thought the other day because I was being attacked about my theory on angular momentum, complex angular momentum spins changing to linear momentum. And I thought, really, you don't even need to go there in order to explain where inertial mass comes from, because if light is a constant speed and the subatomic particles are electromagnetic energy or light spinning at the speed of light, and then you were to move it in one direction, you would be speeding up light on one side, slowing it down on the other relative to you, changing the relative speed of light or time dilation in the object, and maybe that's where the inertial mass comes from. So it's just another way of looking at it. What do you think of that?
Sounds interesting. That actually sounds more physical than other things you can do. But I don't know whether it's true.
It would be another way to explain Alzofon without having to go into the whole angular momentum, complex angular momentum spins become linear energy. So it's just another way of explaining it. And it's something I'm finding with Alzofon is there's just so many ways to explain the experiment that, like, I don't think the theory has to really be correct. We just need to get the experiment to work.
Yeah. That's one big thing is that all these different paths lead to all roads lead to the Rome, basically. It all comes down to rotating nuclei very fast and nucleus very fast, and then effect should turn up. Or whether you kind of believe into Alzofon or you believe into these patents which came up recently, or when you are talking just about mass defect and binding energy of nucleus, which is my line, or like Todd's, it all comes down to the same thing: spin the nuclei. And there is only one way to spin the nuclei with electromagnetic waves at Larmor frequencies. So it's my original idea came actually from how microwave work and how a piece of chicken is hitting in a microwave, because what's happening, microwaves in a microwave are spinning water molecules. And that was, my idea literally comes from heating up a piece of chicken. So for space propulsion.
Oh, okay. Dejan, we plan on having a get-together here at the lab probably sometime in April where Todd's going to be coming in. Jeremiah, you weren't on earlier, but there's a chance we're going to get David Alzofon here at the lab for the Alzofon experiment.
Oh, excellent.
Dejan, would you want to fly in? We got a budget for visiting scientists and engineers. We could put you up at the lab house or at a hotel. All expenses paid.
That would be really
What?
nice. That would be really nice. No, I would be interested. We could talk about it.
Yeah, we'll definitely talk about it off air. Oh, we got something going on here. Is this Jeremiah?
This is the.
Hold on one second. Let me spotlight you and get you spotlight for everyone. Let me make sure that we got it on OBS. Okay, go for it, man.
Yeah, I'm looking for it right now, and there it is. Let me open this up. Boom, the Nasicus Wavy capacitor paper. Okay, let's take a look at this. So here, Nasicus talks about an interesting device. This is why I love this thing, because you can use low-K dielectrics at very, very high voltages with this geometry, and the dielectrics can be made of one material, which is also really nice. Now, ideally, it's actually made of two different materials. On the backside, this would be a low-K, low-mass dielectric, but this would be a very, very high-K dielectric here in the Wavy side. But basically what happens here is that we have this internal plate. You see the black line on the inside? That represents the internal plate, and all this is connected together as one piece. It can actually be hollow or contain a vacuum or whatever. And then there's this dielectric here, one dielectric and another dielectric. They can be different or the same. And then this outside case is all one solid case, and you can ground that, meaning that this case can operate at a zero potential, which is why he calls this propulsion of a wavy asymmetric capacitor having a zero potential casing. So you don't get shocked, and you can put this drive inside of anything effectively. But to make it, you need a wavy capacitor. So in order to make this plate, which is kind of a bead to make, he talks about in another paper of his that the dimensions of each of these loops here, these bottom circles, they are 1 millimeter across. The points from here to here, that's 2 millimeters, and the depth of these slots is 2 millimeters. So this is what I came up with. And I have it underneath a piece of glass, so that's my wavy plate. It's aluminum foil, and on the back side, it's copper tape. And then this little square pad of copper tape is going to go on the other side of the dielectric. So That forms my wavy shape. It's almost the same dimensions that Nasika specifically talks about using in the patent. And what he calculates out of something like 4.9 or 4.7 grams or whatever of force for, what is it, like a 10 centimeter square or something. I don't remember exactly what the force is, but it's pretty damn high anyways. So even this thing at about 30 to 50,000 volts should potentially produce upwards of 1 to 2 grams of force if his calculations are correct with the dielectric constant material of 1. Which is what I'll be using, epoxy and other materials. So I'll sandwich that between 2 pieces of plastic following his papers, and we will see if it produces any force. But it will be really awesome if it did.
That would be amazing. Question for you, Jeremiah. I noticed that the in the patent, the 2 dielectrics had wavy patterns that were going in different directions. Is there any specific materials that need to be used, or 2 different types of dielectrics?
No, basically what he talks about is that you can use high-density polyethylene or polypropylene or any other common plastics that are available that have a reasonably high insulating value. So it's not necessarily about, because a lot of the plastics, they're not really going to have a high dielectric constant in general. They're going to be probably between 1 to about maybe 20 at the absolute most for some really phenomenal plastics. But it's still, these are not particularly high numbers. But what they can offer is really, really good insulation, in the many hundreds of kilovolts per millimeter type of thicknesses. So that's really the ideal way, is because you can just get so many charges there at such a high voltage. It does require a really high voltage. Nasikas talks about in that paper, at 4 point something grams of force for his little design that he came up with. So those are operating at 20,000 volts DC, not an AC, just straight up DC. And he says that they'll produce that force kind of continuously. I don't know if I buy that, if I believe that they actually produce a continuous force with no power radiation, where another paper that I was reading, having nothing to do with Nasikas, talking about asymmetrical capacitors, talks about the absolute necessity of ramping a high frequency AC on top of that DC in order to radiate some power. But the difference is the power is not radiated equally from both plates because their surfaces are different and the geometries are different. So the vectors of radiated field, they don't end up actually balancing out forces when you ramp it with a high frequency. And so that's one of the things that I might try if with DC it does nothing.
Okay, we also try NAM's power supply as well. And
right, because that does exactly that already. Just at 60 hertz, but hey, it's still an AC riding a DC. Oh, I forgot to mention, it also does it at whatever high frequency that driver is at. That's probably 30 kilohertz or something. So yeah, we do have that. That should be enough.
Sweet. So when are we going to see that experiment being ran? Is that?
Well, I will be epoxy encapsulating it tonight, and then come tomorrow, because it takes so long for that freaking epoxy to cure, man. It just absolutely crushes my poor soul because of how long it takes to cure. But, it is what it is. It's a 24-hour cure in order to get the full dielectric strength and full cure out of it. And I do use an oven to speed it up, but still, you can only make it go so fast. Anyways, when that's done tomorrow, I will put the plates on the outside and then terminate the high voltage wire. And I may even get a chance to test it tomorrow, sometime about maybe 4 or 5 hours from now tomorrow.
And the material that you're encapsulating, if you had the kiln capability, could you fire it into a solid ceramic mass without?
No, I do not have the kiln capability. Even if we had a kiln, which we do over at the Falcon Space Lab, have a kiln that's used for curing dental implants. So,
right.
But it gets up to
I'm just
1200
asking
degrees.
But
the thing is,
if you had it, would it be possible, or would that stuff not fuse together?
Ideally, if we could make our own CCTO high dielectric material in that paper, Nasika says that if you get a really high dielectric constant material, force goes up from like 4 grams over that same area to like up over 400. So, yes, it would be great. I don't know for sure if we can do it because we have not tried it yet.
You can hit 3,000 degrees with tungsten wire for resistance if you're using it in an argon environment. Like you can actually get a higher temperature before it fails in argon than if in a vacuum.
But to be honest, we are not geared up for that kind of work right now. if we were, we'd be making our own superconductors to try to meet the Polar experimental system where he's got like these materials added.
Hey, listen, I'll keep you tuned. You know, I'll keep you like, I don't know, informationed up because I'm working on that right now.
Yes, that would be super awesome. If you can print ceramics that act dielectrically, at least the same way that high temperature ceramics do, it would solve a whole world of problems for our experiments. Especially if you could choose different ceramic powders. Like if you could get that thing to print CCTO or whatever binder or material that you use to hold it together did not significantly degrade from its properties, then I mean that would be remarkable.
Yeah, I was looking at the like molybdenum disulfide electrodes for heating and whatnot, and the silicon carbide for like using like a, you know, microwave energy to basically, you know, use that to generate heat, cause the silicon to heat up and release the heat. It seems like the best element for heating to resist the highest temperature is going to be something that's tantalum and hafnium carbide. So that's going to be the ultimate goal. But at some point, I should soon have something that's running tungsten and at least in a zirconium brick kiln. So it may take some damage by running it all the way up to 3,000 degrees, but it'll survive long enough to basically hit that long enough to fuse things together and just have to replace the bricks, which I have a ton of them here that I just have to go get more of them. Like I said, that glass plant's just tossing them. So
I don't know, man. Maybe the argon will save your bricks.
Guys, there is some really good stuff going on here in the live stream. We don't have that many viewers, but the people who are posting here, we got Esoteric Gold, who
that guy knows this stuff too.
He
actually, you know, Peter and Esoteric both in there know that.
They know their shit, whoever these people are, and he's at Esoteric Gold is working on some sample that was sent to him from Arizona of monoatomic copper and at least 1 or 2 samples of monoatomic gold, and it should be ready in a few weeks. He plans on sending us some samples.
Oh yeah. That's awesome. Very excited about that. I can't wait to start experimenting with that stuff.
Peter Middleton just wrote something very interesting. He said the permittivity of ultra-thin metal foils is infinite. So how about stacking thin film, high-strength dielectrics and metal leaf together? Then you could have high voltage and high permittivity in one package.
Well, that's exactly the point of why you want to add all these really fine particles into your dielectrics, if possible, these fine conductive particles. This is why Brown wanted heavy conductors inside of his dielectrics, fine little particles of lead or something else heavy. This is why bismuth powder is also useful for this. This is one of the things that may also be relevant to Van Dert, where he uses fine metal particles, again, suspended at some distance apart from each other, because all these things, they increase the permittivity of the dielectric, whatever it is, drastically, because they have the ability to focus and concentrate on an electric field, each of their own, once they acquire a charge. And so absolutely, yeah, I'm thinking instead of layers, which would really work well, layered materials would work well, but also just having simply fine metal particles within that structure should do an equally good job.
I'm loving this. Yeah, it's just, it seems like going for really thin materials gives you these unique properties, and dealing with the near field interactions, that's really where it's at with the propulsion side of things.
I'm wondering if you use stacks of thinner material, if you can get more resistance out of it than you would get out of a solid mass.
Are you talking about dielectric strength?
Right.
Yeah, that's definitely the case. We find that the dielectric strength of materials is nonlinear, and it weakens the thicker you make it. So you're better off with thin layers.
That makes me think that there's some like connection to
well, it's the electron mechanism. Think about it this way: once the electron finally does manage to tunnel its way through, say an electron is at a spot of the dielectric where it's about to break down, and it wiggles its way a little too close so that it has too much attraction force, and now it begins to accelerate. The more that sucker accelerates, the more heat it generates. The more heat it generates, the weaker the dielectric becomes in the surrounding area, so consequently the faster it breaks down. And so the thinner the material is, you capitalize.
What about the fact that it's generating more than heat, though? And that
Well-
might actually be increasing its mobility more than the heat allows it
Right. Well,
to move.
exactly. It is. It's not only
Which-
just generating the heat, but it's also accelerating the entire way along.
Right.
And so, of course, the
magnetically-
thicker that you make it, the more easy it is for that one cascade to break down the entire material. So if you just want to capitalize on the pure properties of the dielectric without worrying about the effects of electron momentum or thermal capabilities of the material, just say it's room temperature, static, regular properties, you can optimize those by making it thinner so that electrons, if it does break down in one layer and you have lots and lots of layers, dielectric.
Right, it's got to jump over
conductors.
all of those layers and it's losing energy every time it jumps a gap.
Exactly, and
Well,
that's how you
the other
can
thing
really
that I'm looking at
capitalize it.
though is, I mean, why do we stack transformers?
Well, what do you mean stack transformers?
When we make transformers, the best transformers are stacks of metal.
Oh, you mean why do we use laminations instead of solid pieces? And yes, it's exactly the same reason. Eddy currents within the material in order to eliminate them.
Right. So it basically reduces that drastically by building those layers because the eddy currents start interfering with each other in each layer in order to basically cancel them out. The layers of the dielectric might be doing the same thing with the electron mobility in the first layer, maybe causing electron mobility that's in reverse and basically is going to resist that. So it kind of pushes back to keep it from poking through. It's definitely something that we should probably have. We need better electron
Hey,
microscopes,
I see
man.
that, Thomas. That looks like, hey, show me that core again, Thomas. Let's take a look at that. Hey, guys, take a look at Thomas's little core. That I just missed it. Yeah. I can't see it on the screen right now for some reason because it's just showing me everyone else's video. I guess I have to figure out how to like scroll up and down, but for some reason I can't. Oh, yeah. Oh, that thing. Yeah. Okay, there we go. That I just didn't get a good look at it.
You want to see the
armature.
magnet that goes to it?
The ring magnet? Sure, why not? That's nice.
Ring magnet. Wow, I never seen such.
How many poles are on that? That's 12 pole?
We
How
got
many
it. We
poles
got to
on
get
these?
our focus. Focus is
I'm
off.
guessing it's probably well. It would have to. I think this would have to be like 11 or 13 poles because I think this is
that's right.
12 coils. So it's a 3-wire hard drive motor. So.
Oh, cool. Yeah, that makes sense.
But.
Oh,
One
so
of
Sorry,
those
I
things-
scrolled there. Interesting, though.
actually
Peter
cutting
Middleton
the,
just mentioned something really interesting. He said the problem with nanometal particles in bulk dielectric polymers is the dielectric strength of the polymer. Synthetic nanodiamond powder as the filler has a dielectric strength of 1,000 volts per micron.
Holy man! Wow. Okay,
and
well, we
diamond's
need
not
to
that
figure out,
hard to
can we buy this
deposit on
powder?
things. Actually, no. It's not hard to build a diamond layer on something. You just need a combustion chamber to basically burn the stuff down in a reducing environment. Don't allow it to the gases that you're using like methane or whatever to basically oxidize, so that way you're not getting carbon dioxide and it'll deposit on the surface to form diamond.
Wow.
It's like one of the only ways you can make diamonds without a massive amount of pressure to squeeze on the stuff in order to basically force it into that.
So you did I just hear you right that you said you can deposit diamond on the surface of metals?
You can deposit carbon in diamond formation by decomposing like methane and propane and other carbon-bearing gases.
So
it's
would
just
you
like
say that
intense
you can
thermal
form like
decomposition.
sheets of this
Right.
stuff that way?
Right. It's real slow layering, but if you're just building layers in between your dielectric, each layer would basically, drastically increase the capability of what you're doing, and you'd be doing what you do. You make that material that I just had out that I was showing you the conductivity with the aluminum layer and the plastic
Oh
layer.
wait, you're talking about CVD graphene, aren't you?
Right. But it's not graphene though. You're talking about a solid layer of diamond. They do it on windows to basically put a hard coating on it so you can't scratch it.
Really? Wow,
So
I
you
should look
should
into
be
that
able to do that.
process more. I'm not familiar, and I feel like I should be already.
Well, I'm wondering if we can marry cold plasma technology in order to reduce the temperature further so you can work with plastics without damaging them and you're still building a layer of diamond on it.
I mean, because it would be awfully cool to be able to print, 1 micron thick or 2 micron thick layers of diamond as dielectric to try to make some of these devices.
Or however long you want to let it run in order to build up whatever thickness of layer. And if you can alter the properties just slightly as you're going, you could get layers of graphene in between there. So that
That'd
way,
be
if you
wild.
need more strength to hold it together, it would give more flexibility and more resistant to being snapped and broken while it's still a rigid chunk of diamond in between those layers of plastic. So as much rigidity as you can get at that thin of a layer of diamond. That's going to have one hell of a bend radius with it being that thin before it snaps.
That's just wild. That's just wild. I mean, I'm just imagining you could print layers of graphene onto your friggin' diamond, right? And you could effectively form different dimensionalities of materials and control the entire field geometry within a dielectric. It would just look like a completely clear piece, but in fact, it would have these sort of arcuate curved pieces of graphene inside of it, and so its electric field would be really asymmetrical. But you'd never be able to tell.
I was looking at doing something similar to this, where instead of it being solid sheets, each layer had openings in the diamond, so the graphene was coming through it to make bonds to each layer. That way you could make a touch screen, make a capacitive touch screen, but it was made out of stacks of graphene and diamond that were extremely thin, so it'd still be really hard to scratch, but it wouldn't crack and break. It'd be just as flexible as a normal piece of plastic for, like, say, a cell phone that has to survive. You know, you're going to be taking it to space. Might have to use to stop a micrometeorite or something, you know.
Mm-hmm. That'd be amazing. We need to get on these, like, new materials.
There's a way to dope graphene too when it's being grown to stop it from being a conductor too. So just like you can make semiconductors and all kinds of things with it, so there might be a way to make a better dielectric than even the diamond by just basically doping the graphene. But in the meantime, other technology is known. It's been used for years, so it wouldn't be that hard to grab what they know and adapt it to whatever it is you're trying to build with something as simple as like that kiln that will run up to 1200 degrees. So
that would be awesome.
Peter's like ahead of the game on everything. He said CVD diamonds, super dielectric, and superconductive graphene layers. Like, you can use carbon for pretty much the superconductor and the super dielectric.
Heck yeah, absolutely. That's the idea.
Carbon is like the Lego blocks of the universe.
Plus,
yes, all we have to do is reorient the direction the bonds are facing each other, and all of a sudden the properties are completely different. You gotta love it.
Okay, guys, I need to sign off because I want to work a little bit on a project.
Same here. It's time for me to put the case on this thing. So let's probably finish it up, hey?
Okay, let's finish up. Go ahead.
Jeremiah, message me with the geometry, the like external geometry of that thing you were needing the graphite mold for. That way cool. I can see if I've got a block that will suffice for that. So.
Yeah, my goal is to have two pieces that clamp together very, very evenly to form a flow mold so that I can make bismuth wires if possible.
You're going to layer something in between them and clamp the two together so that way you can charge each one independently. Like put a
well, in the
positive on
first
one
case,
side,
I'm just gonna. I just need to initially make the wires, which I can just cast through that stuff and let it cool. I could actually have it hot enough to the point where I could slowly cool it down if I wanted to, and have it crystallize, or I could hopefully cool it more quickly, and it I don't think will crack if I just air cool it with some forced air. So it's pretty resilient.
I can run some tests on, like, as long as I have more than one piece, I can make a mold and do some tests here, because I've shown you I've got like that other piece. I have a couple other pieces of that bismuth, so I got like 15 pounds of bismuth around here somewhere.
What we really need to figure out, Thomas, is how we can make some super, super thin bismuth wires, because they have unique properties and they are damn near superconductive if you can get them thin enough.
Yeah.
So it's very difficult.
What about plating copper? What about plating copper, like tinning copper with it? Really
with bismuth, to increase the conductivity? Yeah, if you can put a thin enough layer of bismuth
hair
on it.
Fine, yeah.
Exactly, yeah.
You could
get the same
property. You are halfway to making a functional spacecraft.
I think that our team actually stands a chance at maybe doing something that genuinely moves the species closer towards that goal. If anything, we might just help the human race get that one step closer towards Star Trek. But
yeah, we need the replicators. We got to be able to stock the ship with that, so that way, if we're making a longer trip, we can definitely take care of ourselves, or whoever's out there doing whatever they're doing, because you're going to run into problems no matter what.
Yeah, absolutely.
There's a lot of unknowns out there. I don't care how great the travel technology is. If you can't repair things on the fly, you can't just call up AAA.
Okay, guys. So I'm off. It was nice listening everybody's ideas. But let's do some work today or go to sleep. Because for you it's very late, I guess. For me, it's just starting. Okay. All the best. Bye.
Thanks, Dejan.
Good talking to you.
We'll stay in contact. This guy, Peter Middleton, he sounds really knowledgeable. He's out. He actually works in the UK sometimes, and he's out in an island out there doing his work. But he knows a lot of shit about material science.
Yes, he does, man. Peter has educated me quite a number of times and has sent me a huge amount of information. It's just great info, and it's like, what, that exists, and whoa, that's cool kind of stuff. You know, it's exciting science and papers and things like that, all relevant to what we're working on.
I want him.
Graphing.
He's gonna contact me. He promised to send me an email with his contact info. We'll get him on the WhatsApp group so we can have that's what we need, is the continuous conversation that's going on at 3 a.m. And hey, we're middle of this project. What's the material
we need better
science?
shipping too, man. Much better shipping. I'd like to make some of those discs and send to Nam and see what he can do with those. Like build the stacked layering of the different materials, because I'm already making something that uses that same process for a completely different reason. But there's some like very unique properties you get from that. Like I said, I took a piece of 3/1000ths of an inch thick steel, and I put a little rosin on the steel, and then hit it with the soldering iron to heat it up, and melted bismuth over the surface. And I thought it was thicker than it actually was, because when I went back and measured, the whole thing was only 0.004 of an inch thick. So it was only 1,000th of an inch of bismuth. But the difference between the two halves when I was approaching it with a magnet was literally like 3/8 of an inch, because it was like 1/4 of an inch before it started attracting it to it when the bismuth was facing it. But when you flip it over with the steel side facing, even though it's only 1,000th of an inch closer, it was attracting to the magnet at 1/2 an inch, enough to actually bend the piece of shim up toward the magnet to try to
get out of here. Oh man,
wow.
That is wicked awesome.
Well, and I think there's a simple explanation for that, and that's that you're activating the diamagnetic property of the bismuth if you're approaching it first. The iron is going to mimic the bismuth's magnetic field, so it's going to create more diamagnetic pressure until you overpower and saturate the steel with the actual magnet's power instead of the diamagnetic property of the bismuth. So
good point. No, that may very well explain it. I mean, it's interesting that you have a theory too, but that's just that experiment alone, I think, is really super fascinating, and I love the idea.
This is the thing. Neodymium magnets are so powerful because we're literally using a ferrite magnet that has, like, on every single crystal, there's basically a cap on either end of these crystals with neodymium to focus it, and then there's a boron atom, which is basically diamagnetic at the core. So you've got 7 chunks of 7 atoms of iron on either end of this. When they're made in a completely crystalline formation and then ground up in order to break those crystals apart and center them together, when you hit it with an electromagnet, you're forcing those crystals while they're still in their shape to rotate around, instead of getting deformed like there might be 9 atoms of iron on one side and 5 on the other, where you end up with this dissimilarity on the sides and whatnot. So you can't get as uniform of a magnetic field flow through it. So stacking the steel in between the aluminum, which is also, it's not I don't think it's as strong as a paramagnetic material as neodymium, but it is a paramagnetic material because they use it in supermagnets too. What is it?
I want to try that experiment you laid out earlier of taking non-magnetized neodymium and sticking it inside the electromagnet to remagnetize it. So I got this little neodymium magnet over here. I'm going to measure its Gauss reading with the Gauss meter, heat it up to the Curie temperature, use my little blowtorch, and then we'll make sure there's no magnetic field, and then I'll stick it in there and see what happens. You want to stick around for that?
Cool to see. I'd like to
Yeah,
see
get
what would
it,
happen if you
Jess.
just stick it in and magnetize, but charge it the other direction.
Oh, we could
Pop it once to demagnetize and pop it a second time to force everything to finish rotating around. See if it's strong enough to do it.
All right, let's do that. I can only pump it up right now to 0.86 Tesla. That's the, I think it's the voltage, no, it's the current limit of my power supply. It goes up to about 40 amps. So it's pumping around 1,000 watts in, or a little bit less, more like 800 watts to give me 0.86 Tesla.
Okay.
So let's
While you're doing that, I was gonna say, Jeremiah, something that I thought of that might actually work since you're trying to make wires is using the carbon as like a draw plate and heat it, because bismuth gets brittle whenever it's cold. So drawing something down like that, it would basically shatter. It wouldn't draw through like, say, a piece of copper that's much more ductile. But when it's hot, it would be able to be drawn. So I don't know if that might help in order to get much lower on the the diameter of your wire too. So that you get a size started and then take that and use a second plate that's actually got basically draw plates. You sandwich them together with like a half hole on either side. That way, if they wear or something, you can use like sandpaper to relieve some of the material in order to shrink the hole back down again and make sure it's tight. I don't know what.
I mean, it will be ideal. It doesn't just have to be wire either. If I can make a thin enough plate of bismuth, but the thing is, it would need to be sort of cast super thin or deposited super thin. Ideally, even vapor deposition would work. But
right.
Just having that super thin layer of bismuth is ultimately what I'm looking for.
Right. Well, there's another thing too. I noticed that bismuth is it's really hard to dissolve with acids.
Is it?
With the exception of vinegar. Acetic acid eats away very quickly. In fact, I have some of this white milky stuff that I don't know what it's done to the material that the canister is made out of, but the steel, it's actually started dissolving the stuff in the lid. But it was basically just vinegar and hydrogen peroxide and a real fine powder. And that's what I ended up with, minus the orange and red stuff that's coming from the iron now, which you can see on the top. It's coming through like that. But I mean, this is like a 5-year-old experiment.
Guys, check this out.
Well, I got 99% acetic acid, so if it comes down to having vinegar, and vinegar is acetic acid, we should see some pretty reaction.
Well,
quick reaction, yeah.
This isn't a high concentrate. This is just
fully
vinegar.
demagnetized
It's like
magnet.
6%.
Right. What I mean is, we might want to speed that 5-year process up a little bit, for.
Oh no! This didn't take 5 years to get this.
Oh.
The iron is what basically precipitated over that period. Like, it's been sitting like this for 5 years.
Oh, okay, that's what you mean.
But that chunk of reddish black material in there and whatnot, that was not in there until I think the last time I looked at this that it wasn't in there was probably maybe 3 or 4 months ago. And I hadn't looked at it, in all that time. And then I looked today and saw that, and I was like, oh crap, what's that? That shouldn't be in there, because I was trying to figure out what it was, and then I realized because of the lid, with the way it's breaking down, that's what that brown and whatnot. In fact, you could see the spalling coming up on it.
Nice.
The iron in the lid going down into it. So it lasted a whole lot longer than the sulfuric acid process, where I had to add hydrogen peroxide with it. But my point is, if you were to use the rosin process to coat, say, a piece of steel, piece of copper, or zinc, or any other metal, that you can just basically, to tin the surface of it, you can then etch the metal that you applied it to, so that way you would end up with just the foil of bismuth, because of its more resistance to many of the acids that the other metal would not be resistant to kind of refine it away from it. So it was something I thought about using for making aluminum oxide nanopores through anodizing, and then get rid of the aluminum by just etching it off, so that way it's actually a sheet of aluminum oxide pores. So completely open all the way through. So it should work for something like that, though, fairly easily. So it might even work with the wire trick idea that I was talking about too. I'm not sure how, you probably have to just tin one side of it. and then squeeze it afterward in order to force it into a wire shape after the mat is stitched away. You don't have any rolling equipment there, I guess, for like rolling wire and sheet and stuff like that.
No, and I mean the size that we're talking here is as thin as I want it is probably far too thin to roll it.
I wouldn't say that. Trust me.
No.
I've been rolling lots and lots of stuff. I made a tool for my, like I showed you the rims for my goggles, correct?
Yeah, I believe so.
It's got a ridge sticking out of it all the way around.
That's nice, dang.
So it's just a flat sheet, and then when I'm rolling it to put the rim on it, I roll it. I should say when I'm beading it to put the bead on it, I roll it at the same time. So I'm curling it in two different directions at once.
Nice.
And I've worked with aluminum and stuff like that. That's extremely thin with that tool. So I guess I just need some dimensions, and I could probably throw a rolling machine together and just, you'd have to assemble it when you get it. That way I can pack it down into a box tight. And with what you're talking about working with, some like ultra high molecular weight for your plates to hold the rollers and pinch and unpinch them would be more than enough pressure without it breaking down. So I'm rolling stainless steel, titanium, with tool steel rollers that are just pinched together with ultra high molecular weight and a 1/8 inch thick plate of I think it's 3 or 4% titanium, and the rest is aluminum.
I think ultimately we'd probably want a chemical process that creates a little more even surface so that we're not dealing with mechanical. Because the trouble is that with bismuth, if we're doing that, we're going to have the crystalline structure become affected by.
That's why you need heat.
Process.
That's why I think you're going to need to be able to heat the rollers. That way, it's adding the ductility by warming up the bismuth close to the point of basically melting. Kind of like whenever you're heating up steel and then you pound on it. If you pound on it while it's cold, it spreads out and eventually starts cracking and breaking. But if you heat it up until it's like red hot and then hammer on it, it won't start splitting and cracking around the edges. It'll just form a flat sheet.
Okay, guys, let me just show you what I'm working on right now. I completely demagnetized this magnet. It went from about 1,300 Gauss on the edges. Now it's down to 0. I thought maybe I could
What'd you use to heat it up?
Just a little blowtorch.
Okay.
And this.
I was gonna say a heat gun will do that too, man.
You don't need much.
It's hard to believe how much heat you can get out of just hot air and whatever that. I think it's probably Canthal wire wrapped up inside. It's basically like a hair dryer that if you used it to dry someone's hair, it'd catch their hair on fire.
Right here.
Yeah, that's it. Yeah.
I could have used one of those as well. So I'm thinking of using this little chunk of iron over here as a concentrator, because this will fit inside the air
to draw the magnetic field into it.
Yeah, so
perfect.
Get more magnetic field in there, and I will power this up right now. We'll see what we can do.
Not sure I'd use two of them though. Pushing those two pieces of steel together, they'd probably crush that magnet and break that brittle structure inside.
I don't think he's got quite that field.
I think we're going to go pretty high with this field right now, because
I've got a video I can show you where I basically used a 4-ounce ball peen hammer to basically completely crush a neodymium magnet in order to basically, while it was still magnetized, in order to use the powder to make. I think I showed you the epoxy with the spiked magnetic powder inside of it.
Yeah.
That's how I made that. It was just basically like, it's back there. The head of the hammer is like that big. It was like
I'd like to see that video.
No energy. It takes, I guess maybe it might be because it's all shock instead of it just holding it together. But if that's got enough magnetic field, even if it's touching, might be enough shock to force it together. And then we'd ruin our experiment because we wouldn't know if it magnetized it unless basically the powder's all magnetized and forms like a blob, Something you could basically play with like silly putty because it's all constantly sticking back to itself. That's what the stuff was like. It felt like I was working with like a dry putty, like a granular putty that for some reason didn't have any liquid to it, didn't stick to my fingers. So
that's weird. Interesting.
How long do I have to hold it in the field for?
How is the field been turned on and off? Because you should only have to just pop that thing momentarily.
It's on right now.
Yeah, I don't think that with it being cold, holding the field on it is not going to do anything more than the initial shock of it. If it doesn't have the energy to move it initially, then it's not going to move it anymore. Still no magnet?
I think it worked. Yeah, and it's more powerful than it was before.
Oh,
What?
nice.
Yeah, look.
Nice. It's probably that slug, too. If you'd have just thrown it in there with the
Let's
magnet
take it off the
itself,
slug
it's
mark.
the
Let's
same.
see what it looks like without being on that.
Well, the slug is not attached to it right now, but you want me to run the experiment without the slug concentrator?
I want you to just get another magnet that's not been screwed with and stick it next to the thing and tell me which one has a stronger field.
Let's see.
Retest it so to make sure that the Gauss meter hasn't been screwed up. Now it's
It's always good to
number.
calibrate it against some kind of standard, right? Even if it's another magnet of the same type.
Okay, this magnet is showing me 842 Gauss in the center. This one is showing me about 1100. This is the
The one that you made?
The one that I made is 1100, yeah.
Okay, now do me one more final experiment favor. Put your other magnet that was just 800 back on that slug, the one that you haven't depolarized, and then stick it in that field and see if you can increase its flux.
I just noticed something. This slug is not doing anything. It's not ferro. Like,
Well, that's okay. So you got to replicate the experiment by putting it back in there.
Hold on. Paramagnetic materials still focus a magnetic field. They just can't retain a magnetic field, and they don't react to a magnet in order to stick to it. It's very weak. But when you're pumping a massive amount of magnetic field into it, from what I seem to remember, the higher the paramagnetic state, the more you can saturate it as it's passing through it.
I will
And
confirm
there's
that
higher numbers
right
than you
now.
can get with
Okay.
ferromagnetic materials. So
There, give me a moment. I'm at 8,600 Gauss roughly. Now I'm going to put this piece of material in there. Still 8,600. No, it didn't.
God, I'm waiting for him to pull back, and he's going to be missing a finger or something.
No, nothing happened.
That just worries me, man. Those are some massive coils. I wonder how much of that is the plate stacks, but I'm wondering which is
This isn't
which is
doing
which, like
anything.
how much there is in there,
It's not doing anything.
and how much is housing.
Let me see if we got something that is ferro magnetic that will fit the gap.
That didn't stick to that slug before you put it in there, though, right?
No, it's the.
Okay, you had to tape it onto it.
I had to tape it onto it. Oh,
That'd be if it was
is what-
magnetic
this is-
before
this
you
is,
did that, and then it
ferrous.
stopped allowing it to bond to it. That would have been something we definitely need to look into. See what that magnet did to it to stop it from being ferromagnetic.
This is
Yeah.
ferrous.
Be interesting if he had a way to basically make ferromagnetic material, because that's apparently really difficult to make.
Jeremiah, using this magnet, we can create our own custom magnets if you want to change the orientation of the field now.
Wow, so did you increase the strength of that field, or did you flip it?
I don't know if I flipped it because I didn't measure which side it was, but I could have flipped it. I could have changed the orientation. Whatever I wanted to do, we can do.
I think the temperature of the kiln you guys have is high enough you could crush the magnets up. You'd have to use like a box or something and put argon in it so they're not getting any oxidation on them. But put them in a press them into a mold and then stick them in the kiln and fire them to reform them into a different shape. So if you can do that, then you can take a bunch of little ones and make one big one if you want. Make it whatever damn shape you want.
I'm trying to think if there's
Indeed.
a piece of iron here in the lab.
You guys have a press around there?
Yeah. That's
Like
what
a
these
hydraulic
pieces of
press?
material are for, actually. They were purchased for a press to press together the high K dielectrics.
How many tons?
10 tons. It's like a tabletop 10 ton.
Okay, that should be more than enough then. As I'm pretty sure that like even a 6-ton A-frame would work for that. That's one of the reasons I got the A-frame I've got. So
Jeremiah, do you remember if I have any iron here in the lab, like something that will fit 2 inches or less? I could probably use a pair of pliers or something like that, but those aren't very. Not really.
Well, we were just stacking a crap load of washers, honestly. But
That's a good
those
idea,
collars
washers.
that go around those those collars that go around those press pieces,
They don't fit.
that don't. What's
wait,
that?
what are you
They
talking
don't-
about doing?
We're trying to concentrate the field to try to make the magnets even stronger. Let's see if we can get it to.
Damn it, man! Why do we not have a Stargate?
Yeah, what I was saying, Mark,
I
is
know
that
damn well I have something here. If I could just reach my hand through and hand it to you, you could definitely use it. You know what I'm trying to think of the name now. It's a pin for the pistons in engines.
A pin?
No, it's not a cotter pin. It holds it onto the actual rocker arm itself, right?
Oh, I know what you're talking about, and I'm an idiot for not knowing the name of it.
I have a box of those things that came from a motor rebuilding shop.
Are you
right?
talking about this kind of thing that I have on the drill bit here?
That'll work.
No, but that, yeah, I was gonna say that might work there. Yeah. God, what did I do with that now? Hell, here they are.
What if I stuck this big?
Yep, definitely it, because it's heavier than hell.
What about this magnet? If I stuck this guy in there?
Hey, man, that might help focus the fields, but don't put it in there backwards. You got to get it right.
See ya.
Oh yeah. They might be a little too wide though, because we need all I got is 2 inches to work with, and it has to be less than 2 inches.
Some
Damn,
of
Mark,
the
I'm
really,
so
really
sorry to
small
hear that.
diameter ones.
It's
I'm
still,
sorry, that was
it's
low
bigger
hanging
than
fruit.
yours. It's
Hey,
infinitely bigger than
I
yours,
have carbide bits, and I
Jeremiah.
have a lathe here though, so I could turn this down to make it fit in between there. Make a couple of them so they fit together and leave some room, because I have a rotary table. I can actually control the rotation, and I made a what do you call it? The hand rotary tool, the pendants.
Yeah.
Made by Fordham. I've
But,
got
you know, what Mark needs is just one of these, man. This is all he needs. That right there. One iron slug.
Yeah, that's exactly what I
right.
need. Oh,
Yeah, see, I have drill stock
How about
here
this?
I could cut a couple pieces off to do that. So
It's a little thin, but
I need something more like higher purity iron. What do I have? Oh, I actually just got some in.
something like this.
yes.
Yeah, but
That's exactly what he needs.
more of a cone shape. If I got a cone.
Okay, now, Thomas,
No,
it's
no,
time
hold
to
on.
stop faking it. Pull out your Stargate and give it to him already. Wow, man, nice job, dude. That is super sweet. That's what we did to the faces of his electromagnet on the Spintronics rig. Electromagnet, we
making-
polished him like that.
That is for making graphene.
Hey, Mark, are you seeing this face that he polished? Let's show him again. Look at this.
Sweet.
Remember having to
This
do
is
that?
done by hand too, though. If I take the power tools to it, I can get rid of all the little ridges and whatnot from turning it down. But this is to basically go into a hydraulic press while there's a rotary table underneath and a motor hooked up to it to keep it spinning around while the top part is held still, while there's graphite trapped in between the two, grinding that material away to force into a flat sheet. So it had to be as flat as mechanically possible, so that way I could start the building up of the layers of the graphene as they're forming on the surface, and then fill the full stack up, so it's just a stack of sheets flat. Better than highly ordered pyrolytic graphite.
Well, I'll be honest with you, Thomas. I don't think that's going to be anywhere near flat enough. But I
No,
think
it's
keep on
not
going.
done. Yeah, it's not done. It needs to be finished, but it's one of those projects, I mean,
Absolutely, it's a
one
really
of these
cool
days.
project.
You want to see something interesting about this, by the way? I didn't notice this until today whenever I was actually messing with it, trying to figure out what was going on here. Let's see. Let me turn this other light on. I don't think I'm getting enough light on this side here.
What's that there? Peeling?
It's another layer of graphite that they fused together onto this other piece. If you look, you can see where it's broken off here. And they sawed that off, but the other side, you see how smooth that is?
Yeah.
That layer underneath there is also that smooth.
Whoa.
I don't know what the deal was with that. I'd have to contact them and find out what they were doing with this. Maybe send them a picture. That way I could find out what's going, because all the graphite's got different grades. This is all, like I said, is for EDM machining, So
Hey, do me a favor of that. Would you mind doing me a favor and checking the surface resistance over a given distance versus the edge to edge or side to side resistance? Because I'm saying assume that it is sheets.
pyrolytic.
Yeah, exactly.
Well, let's say I'm pretty sure this is just basically standard graphite that's been sintered to make sure it's as dense as possible, and then they just basically needed to build it up or something. But I would definitely like to check that out now that you mentioned that. So
yeah, I'd really appreciate it if you could let me know, because if that stuff is, then damn.
actually, if it was highly ordered pyrolytic graphite, I get one hell of a reaction from this magnet.
Do you?
Nope.
Here's some thin sheet of bismuth that I made just by spilling it on.
Actually, it wants to
table.
stick to it. It's not actually, instead of repelling away from it, it's trying to like pull down to it. Interesting.
That is interesting.
I wonder what happens
It's
if you
not
stuck
much. It's very little
bismuth.
pull, but I mean, it's discernible. So
If we stuck bismuth inside the field, do you think it would weaken the surrounding field or strengthen it?
I had somebody tell me that when he encapsulated, like he made a sleeve and put it around some magnets, that the magnets slowly lost their field. I'm wondering if he used heat to melt the bismuth and poured it around it, and the heat was actually what weakened it. He just didn't notice. Because I don't think it'll actually alter the neodymium magnet's effect. I don't think.
Well, I don't know why he wouldn't just put his magnet into the sleeve afterwards. Like, why try to cast it around the thing?
Yeah, I don't know. I don't know. I don't remember where I was talking to the guy. I don't know. It might have been over Unity Forum, or it might have been over on the
You
alternative
always know
energy
you get good information
group.
from over Unity forums.
But
Their scientific method is very rigorous. I'm saying that facetiously.
Oh yeah, absolutely. You know, they're going to be the. And yeah, okay, I'm done. I'm not going to say anything more. Anyways, there is a lot of interesting stuff going on there. It's just unfortunate that there's also so much that's.
Okay, so we had some questions about bismuth going inside the field, and I'm about to give you an answer what will happen. I'm going to get the thickest piece of bismuth I can fit in there.
oh my God, get the safety glasses, man. That stuff, if it shatters, it makes really sharp crystals.
It's not going to go boom. Come on, man. It's a piece of bismuth.
No.
Have you ever seen a piece of bismuth just spontaneously combust when you stuck a magnet next to it?
I got my safety
no,
glasses
nope,
on.
I've seen it spontaneous combust whenever it got tapped on just a little too hard. So
Here,
Really?
I got my safety glasses
it is
on.
extremely brittle material.
Oh yeah, very much so. I usually break it apart with a hammer.
That's why if you alloy it with lead, you can actually get a lot harder material, but it retains a lot of the ductility because of the lead. And this actually, what is it?
I believe
On heating,
is-
it shrinks. On cooling, it expands, and the lead does the reverse. So you can get a eutectic response. so that way it doesn't-
Eutectic material.
Right,
Nice.
that way it doesn't. It's typesetting metal, so that way they wouldn't get any shrinkage, and they wouldn't end up with, like, if they used all expanding material, it wouldn't get bigger and ruin the design. So
Well, that's ideal.
I blew
I'm
the
looking
fuse
at
in
the
lab.
lead, because if the carbon doesn't work, I may have to transition to that's like the next easily available and easy to work with neutral valence material that I've got. So I don't have any germanium, and I have silicon, but silicon would be really hard to work with for, especially trying to form something that would become a resistive conductor to pull that power from that. So
Yeah. Nam's got kind of a cool looking background going on there. He's got that whole bookshelf full of knowledge, and who knows what that all is, or maybe that's like papers for his job. I don't know. It just looks cool. I like it.
Okay, just learned my lesson. We got to turn down the power before turning on this power supply. Cause... Okay, there we go.
did you put the magnet in there with the bismuth?
I'm just turning the magnet on, full power. Now, okay, we're at full power. I'm reading 8736 Gauss, losing the bismuth in.
This will be fun.
All I can say is, at least if it does, chatter and he has to dig some pieces out, he
Okay,
won't be like
I
getting
am
lead poisoning
seeing a
from it.
Okay, can you hear me? I am seeing a change. It's 8736.2, and I'm moving the bismuth in. It is at 8735.
Come on, man. That's well. If
I
you,
think
the
it
question is,
didn't
do
give you any
feel it?
resistance either, right?
I'm swinging it through.
When you
I
pushed
do
it
see
in?
a change, but it's not.
Interesting.
Hey, Mark, I wanted to tell you something interesting. What I did was take my giant stack of Ziggy magnets and stick a little piece of wood, a 1/4-inch thick wood, between those magnets and the bottom of a exactly the same size stainless steel casting tray, and I let the bismuth cool down in the field of the neodymium magnets. So, Ken Wheeler? Is that the guy's name? Theoria Apocrypha. That guy drives me nuts.
Oh,
Really hard to listen to. But he has this idea that if you cool bismuth in an intense magnetic field, that you will polarize it with flux, and that the crystals will be polarized with a crystalline formation.
Whoa,
so
I
you'll
can do that
actually
right
get
now.
better response. Exactly what I was saying is that you should take 2 plates of copper and make yourself a little pouring rig and cool off your liquid bismuth between those magnets. But I do think that you will have to actually have the copper plates hot enough or almost hot enough to melt the bismuth. So at least have them heated so that the bismuth doesn't go cold quite as fast, so that you get a nice smooth surface. Because if those copper plates are cold, it's going to just start to ripple up on it, and you'll have this kind of crappy surface. But if they're hot, it'll be really smooth.
If you can get a controlled, like the grain pattern you get, like whenever you slice and polish a piece of meteorite, if you can get that grain pattern off of that, you really need a laser system to basically create a custom magnetic field on a large piece of magnetic material.
I could do that literally right now.
There's your thing right there to sell, man. Make little plates that say Falcon Space on it that just are formed into crystals. Make them about as thick as a credit card.
I could do that right now. I just need to figure out what I'm going to put the
God, that'd be
bismuth
one
into.
hell of a business card.
A bismuth card?
A bismuth card.
With the grain of the bismuth making the letters and the numbers and the whatnot, and the symbols for email address @ symbol and whatnot. I did something similar with the Mylar where I was basically using heat to create that pattern on it, and the material I had, when you heated it up, it would distress in all these different patterns to form this kind of almost like a holographic looking meteorite pattern. But that was like back when I just got into making body jewelry back whenever Metallica basically made body jewelry popular. So I was at the right time at the right place. We were making like between $3,000 and $5,000 a piece every month off of just making body jewelry and selling it to one store, and they were selling it all.
Trying to think
so
of what
if the business thing
use.
doesn't work, I'll dig up the material so you can get some business cards that have that pattern to it. I need to engrave like a pattern on a piece of copper or something to control the heat over it, so that way you can put the letters into it and still have this meteorite-like look to it.
So Tom, just to confirm, right now we haven't seen much of a change using paramagnetic materials inside the field. It doesn't really change much. The bismuth, it's 1 part to 10,000 that it changes, and this is a pretty thick. That's like a 1-inch sheet of bismuth inside that air gap. I do want to try the the melted bismuth inside the field. What's the prediction on that?
That, like he said, you might be able to control the grain pattern that forms on the surface. So, which means that if you could slice it open and look at the grain pattern, it should change the grain pattern internally. Like this grain pattern happened, just because of the. Here, it's hard to look through this piece of plastic. Let me get it out. But it basically just happened from basically the walls of what they poured it into. Yeah, that just happens from the walls being colder than the middle, so it forms that pattern like that. But if you can control that pattern with the magnetic field, that's what I would be looking for whenever you get done, to see whether it had an effect on it or not. And luckily, it doesn't take much heat to do that either. You got a heat gun there.
We have a metal melting furnace too. I'm just trying to think of what material I can use.
I was thinking of heating it up while it was in between there. Sorry, I'm a little fly by the seat of my pants like that. It's probably not safe to do that.
The thing is, bismuth.
Copper, Mark. Copper.
Right. But the thing is that how am I going to connect the copper together?
You could use. Let's see. What do you have that can handle some?
I have this copper sheet over here, but I think it's a little too thick. I was thinking of cutting out a piece of it and making a cup.
You could use that cement.
Let's say copper sheet would be really easy if you have some screws and a hole punch to basically seal everything up. I wouldn't try to do that with like stainless or anything like that, but the copper is so ductile, when you're squeezing it all together, you can force it to really completely seal up. Just roll it over and clamp it shut with a pair of pliers. So
Yeah, I think think that's the way I'm going to go. So I'm going to take down this sheet and I'll cut myself a piece out of it. Also, I think this is like 1/8 inch.
If you had some of this graphite here, all he needed is a screwdriver. He could dig out whatever shape he wanted to in it. Take a few minutes to carve a shape and then melt it in that.
I could just use the graphite crucible.
Does it fit between there?
I think it might. It's about that size.
That should work then, yeah.
Then we'll have to have a way to get it out of the crucible. Also, if you're doing it that way.
Yeah, you need a graphite mold so that basically you can just clamp it together and then pull it apart afterwards to let it fall out.
Mm-hmm.
Especially since the bismuth swells as it cools off. It doesn't contract. So
yeah, that's gonna break the mold. Yeah, it's
I
probably
wonder if the graphite would affect graphite, or I don't think the copper would affect it since it's a DC field, but the graphite might affect the magnetic field depending on the orientation through the graphite if it's not completely amorphous.
Would the material properties of the bismuth change after?
I don't have the testing equipment to even see if the grain boundaries has any effect different from the core of the crystals that form. So that's something that would need to be looked into, especially if there is something there and you could thicken the grain boundaries. The effect that it has, so it goes deeper into the crystal or something, If it's a real thin skin, it may not be all that useful, even if you are basically able to control the orientation.
Well, having this big electromagnet here in the lab is going to be very useful for so many other things that we didn't even think of when we purchased it.
I'm surprised you guys didn't build an electromagnet.
We did.
Just punch a bunch of brass and stack it up to make a.
We built one. Jeremiah was down here. It was a lot of work, and the homogeny of the field was nowhere near good enough.
Wow.
Nowhere near good enough, and we spent so much time on it, and it was so much work, and it weighs a ton, and it's tiny, and wasn't good. We needed.
How'd you cut your sheets? Because I'm guessing that was probably the most tedious aspect of it, unless you were doing it in stacks.
Oh, we just ordered the parts from the local metal supplier, and then had to machine it down.
They cut it for you.
Yeah, had to machine it down. Yeah.
Okay. So you gave them a pattern, and they just.
They weren't sheets. They were just solid iron.
Oh, it wasn't like copper or brass though. Like a really highly conductive material, and then layers of the plastic that go in between as the insulators.
Oh, you're talking about for the coil?
Yeah.
The coil, we made a custom bobbin on a CNC machine.
You coiled up actual wire onto it.
Yeah.
Okay.
2 bobbins, one on top, one on the bottom, and it was the iron that the homogeny of the field is dictated by the iron. It's less so the copper than more so the iron.
You go with a solid chunks that were formed to the shape that you want them, or lamination?
Oh, Peter just mentioned we should use aluminum foil liner to make it easier to remove. And a heat-proof mold.
No, the answer is no. It's bismuth. If you use aluminum bismuth, we'll amalgam with it in a liquid state. It'll destroy the properties of the bismuth.
That is true, and liquid bismuth and liquid aluminum have similar melting temperatures. I think aluminum.
That's kind of funny. I used
Well, I mean, they don't. Liquid bismuth and aluminum have totally different melting temperatures, but that's not the point. The point is that when bismuth is in its liquid state, it will form an amalgamation with aluminum, even though the aluminum is nowhere near the. And it does that with a lot of other things.
I thought aluminum was a little bit higher, but not that much, right?
It's quite a bit higher.
660 degrees Celsius. So, what's the bismuth, 350 or 400? I don't know. A soldering pencil will melt it, and I can't melt an aluminum can
660
with a soldering pencil that I've got. So they're not quite that good.
Oh yeah, I'm totally off. Jeremiah, you're right.
So
270
amalgam
versus
thing,
660.
though, I'm wondering if it's because of the coating they put on the inside of like the energy drink. Because I just used a piece of aluminum foil and pinched the ends to make a little slug for something I was working on, and it did not react with the aluminum at all. So either that or they might be using like an alloy. Like, I don't know if you know this, but Pepsi used to use a lot of iron in their aluminum cans. So when you go back to sell them scrap, they wouldn't take any of the Pepsi cans. They kick them aside and expect you to just give it to them. The ones from like 7-Up and Coca-Cola and all those other companies, they are pure aluminum. They take them and pay for it by the pound, but their own cans they wouldn't buy back.
Well, get this. So we did something too, a similar experiment. We ended up casting some bismuth slugs into the bottom of soda cans, thinking that was a great idea because it has the right shape, right? Well, after a couple
it actually dissolved it?
Well, no, you didn't. You couldn't tell. It popped out of the soda can, leaving the surface, just there's a tiny hint that it had done something, just almost nothing. Anyways, after casting it twice into aluminum, it will no longer form those crazy colored crystals. It'll still form the crystals. Because it won't form the colors anymore. The oxidization capabilities are gone.
It's building a passivation because of the aluminum that's in it then, huh?
And you couldn't even tell that it had really done anything to the can, but it did something to the bismuth, ruined it.
Wow. Aluminum is really easy to dissolve, though, so if you grind that up, it'd be pretty easy to separate them out. It's amphoteric, so you could use either an alkaline or an acid. Just pick something that won't dissolve the bismuth, and then you can get rid of the aluminum and purify it to get your bismuth back. A lot of work, but...
If we start using bismuth pieces in the space industry as a major frequency, and we end up having a space industry that's huge, then maybe we'll go through all that effort. But quite frankly, you can just buy a kilogram of bismuth for some affordable price. So it's not.
It'd be nice to know, though, if what metals will react with it. If it'll do that with aluminum, there's probably other metals that will react like that with. Just like I was mentioning that the Mercury will react with aluminum and titanium. So, what other metals are out of the question when you're working with bismuth?
Right, exactly. Well, we know that stainless is safe, so at least we know what we can use.
Right, and I guess that the titanium is out of the question, but without testing, we wouldn't know if it has the same effect on it, because I've seen so many things that basically I kept thinking, oh, it's going to react like this because this other stuff does the exact same thing in this way, so it'll do the same thing here, and it's just like completely inversed. I'm like, what the hell? So, and then you have to look at all the information about like the valence shells and all those other crap with the neutron formation and whatnot, just to try to unwind why it's reacting differently. So, and I can figure that out backwards. I can what do you call it? What do they call it whenever you get a hold of someone's technology? Reverse engineer. I can reverse engineer why it's doing it, but trying to figure out what it's going to do with that information, I haven't had any luck with that yet. So it's a lot of work and a lot of math and a lot of basically, some of the physics knowledge is stuff that I only peripherally know. So it wouldn't be something that would occur to me, Other stuff I haven't even read up on yet. So.
Well, that's the trouble, is that you can't really know what you don't know, and it's the constant struggle of trying to find that out.
Right. So it requires a lot of, Edison work, lots of sweat and labor.
It also requires a lot of introspection.
Right. But again, a lot of trial and error, though, I don't know if it'll react like that, so I have to test it. I think it will, but, just to be sure.
Yep,
let's give
absolutely.
It a run. The titanium, it has a much higher temperature differential between the bismuth and the titanium as opposed to the aluminum and the bismuth. So I'm wondering if maybe you guys heated up the bismuth hot enough where it was actually getting the aluminum hot enough that it could start reacting too. Kind of like whenever you hot weld steel together. You get it hot and then you hammer it together, hot forge it together.
Ah, yeah.
If it's cold, you can't do it, but if it's hot, you can actually get it to weld and fuse together. So if the aluminum was hot enough, maybe that was the issue. Which, when I made my cast, I heated the bismuth from on top with the heat gun. I didn't heat the aluminum. So that might be a difference too. I don't know. Maybe I wasn't getting the aluminum itself hot enough for it to react. Let's put it this way: when I forged it, or when I heated it up to flow it into that cavity, it still looked like a bead of mercury. So it was not like no adhesion was occurring at all. It was beating up on it like a drop of water on some wax paper. So that might have something to do with it too. The temperature of the aluminum may have caused it to basically pull away because it's so cold, and it kept cooling it off. It was a really ugly cast too. I needed a slug. It didn't matter, what it looked like or anything. I just needed an electrode that I could stick down in something to use it for electroplating, because I was trying that. And that's when I found out about the bismuth oxychloride, which ruins your bismuth chloride very quickly. Once that oxygen's in there, it screws everything up. Oh, cool. But that's not molten now.
No, but it was molten, and it was cast in a magnetic field. This is one of my bismuth slugs.
Okay.
Oh, you did the
So
same
it works
thing?
pretty well. This is stainless slug, or a stainless steel mold bismuth slug. It's about 3/8 of an inch thick, about 2 inches in diameter. Actually, it's about 2 1/4 inches in diameter.
Do you know what the grade of stainless was?
316.
Okay.
Jeremiah, you cast that inside of a magnetic field?
Yeah, that one was cast inside of a magnetic field using the Ziggy magnets, which I'll switch around and show you here. It's the Ziggy magnets. Huge magnets. They're 2 inches in diameter.
Knuckle breakers.
Oh yeah. Those things scare the living hell out of me. I'm not gonna lie.
My friend down in Dallas has a big box of very large magnets that he had one of them out, and he was carrying it, and a wrench came from almost like 1.5 feet away from him and busted his knuckle trying to get to that magnet.
Man, no!
So
Ow.
yeah, he won't even open that box up. I opened it up to look, and I wasn't willing to pull any of them out and mess with them. They're just all held apart with plastic and plywood to keep them from making contact. It's like, oh.
So that's my high voltage setup for testing. It just runs on, the wires are all over the place. They're kind of a mess because I moved it out of the way.
A very large exposed version of your wand.
Yeah, pretty much. But it's actually much weaker than the wand. It's just made out of parts that were totally recycled. So, like everything on it is garbage poles.
Well, I was gonna say, what's the voltage on the diodes?
They're 6 kV diodes. It's capable of doing about 88,000 volts in total.
Okay. So it's not the 8 kV of the other ones?
No.
I take it that was a special instance you got a hold of those.
The upper stages. See, the first 2 stages, because they get the highest ripple straight off the transformer, I did use these just to sort of prevent early breakdown. And I used a slightly different capacitor there on the first stage that can handle a slightly higher voltage. So that's about the only thing is that my entry stage capacitor, I like to switch that one up, and the same thing with the first 2 diodes, just because the load current conditions aren't the same. It's not a linear device at all. And the more stages you add, the higher the frequency at the ramp. So that thing, it drives at about 160 kilohertz, which is not really ideal. When it comes down to the other supplies, let me pull one of them suckers out. I'll show you.
That's what you use to make your electric, though, right?
The electret?
Yeah, or something like that.
Yeah, we use anything like that. Right.
Okay.
This is another variation. So this is a little modular supply. It's got the 2 resonant capacitors that are just temped on there. Those don't actually belong in the circuit. Normally they would be reduced.
I'm sensing some passion here.
Oh yeah, really? I don't know, man. I don't know what passion smells like, but I know that I like the way this thing looks, and I know that I like when it's all assembled right, that it only weighs 11 grams and produces some, 60,000 volts or something like that. So that's not bad. It'll do also 40-watt pulses. So just imagine that 11 grams of weight at 40-watt pulses, and it will do 1 kilohertz pulse delivery, so it's pretty
Was
damn...
that one of the power sources for one of those deals where you were basically trying to keep from having any wires interfering with it?
Yeah, it's also one of the ones I was
there.
trying to use for the wireless lifter device that can lift its own power supply. And here's one of those other modular micro power supplies. I'll swing it around here and get underneath the light so we can see. And let's see if I can focus.
Holy crap.
Come on.
That looks like it's out of a cell phone.
So that's just one of my little handmade boards. I wish the damn thing would focus, but I can't really. There we go. Hey, there we go.
Very nice.
Yeah, so it's just got a little push button switch on there for now, but that's the modular board. So this is a 40 watt driver board. You can see that the little black squares up near this side, those are MOSFETs, and they're pretty decent. They're good for about 90 amps. They are 6.2 milliohms on resistance at 30 volts. So I cannot complain. Right? And they're super thin.
Well, before I knew just how much power you could run through those things, I got a 4-axis CNC driver board.
Yeah.
The MOSFETs, if they had proper heat sinking, would give me 36 amps per phase. So,
damn.
And it was like a $200 board. Actually, it was before 2000. So it was a long time ago. Prices have come way down since then, but they're not heat sink. They're, really jammed in there tight. So I can only get like 7 amps without them being damaged. So that's still quite a bit though. There are a couple motors I found at, automationindustries.com, that I can run off of that are like in the 22 to 2,500 ounce per inch range. So powerful
for
enough with
price?
a little bit of gearing, you could, lift the car up with it. So
Wow.
You're not going to use it ungeared where it's basically, losing torque because it's holding up a stick that it's, using like an arm to lift up. But as a crane, it would work with no problem, and pretty quickly too. So
yeah,
but
make yourself one of those, Batman type of pull you up automatic winch systems, arm winch.
Hey, right. Well, I was gonna say it's it has to either be a 5, 6, or 8 wire motor. A 4-wire motor won't run because it's all unipolar though too. So, which limits the amount of half stepping. You can only do, I think, quarter steps was the only pull down on it, or the smallest pull down, half and quarter step. And the quarter step is not that accurate.
Yeah, but I mean,
That's
when you're
all
talking
halves.
about just trying to deliver raw torque, does it even matter all that much?
Right. If I were running, I'd need to be able to heat sink them. But if I could heat sink them, I could put big enough motors that for about $2,500, I can put more horsepower into an electric car than you can get in like a Lamborghini Veneno with an 18-cylinder engine. So thought that was plenty decent, So
Car like that would probably scare me to drive, but I think it would be such a blast. I think I just might risk it. Maybe, at like 4 o'clock in the morning when nobody is on the road, just so I can attempt to jam on that throttle on, like, getting on the on-ramp or something like that. Right.
Man, it would be nice to be able to build your own motors like that, so you could control the, use thinner shim to build a larger number of like stacks of your rotor and your stator.
Oh yeah, the thinner the shims, the better the device.
So you can run a 3-wire motor for, just make it a flying car at that point with that kind of power. You just need a power source now to make sure you can keep feeding that hungry beast. So
yeah, you start to get into like the 200 kilowatt range and you have something real decent, and they don't even have to be big.
Right. Something to piss off Paul Muller, considering he's been promising us since 1996 that we'd have flying cars by 2005.
Dude, it is one of my core missions. One of my core mission statements to bring flying cars out there. It is one of the things that drives me forward. I am not kidding about that. Has been for a long time. I want a flying car. Our parents were promised flying cars, which means, I don't know how old you are, but,
Yep. I remember whenever they were... Do you remember the Pontiac Pursuit? Did you ever see that, what do you call it? It's not a demo car. The cars that they take to the car shows, they'll only make them special for that.
You're talking about like the prototype cars?
Yeah, pretty much. There's another term for it. I just can't remember what it is. It was a very eggshell looking. It was like it looked like a hybrid between an eggshell and a hunting arrow.
Eee.
And it never made it to production. Like it was made back in like I think 98 or 97, maybe it was 96. It never made it to production because it had too much external surface area, and they could not accommodate that with the air conditioning. In the sun, it just got way too damn hot. So, but it had fairings over the wheels, all four. So when you turn the wheels, these fairings would turn, and the ones on this side that where they're sticking out would be catching air, adding aerodynamic pull that direction and whatnot.
Oh, that's clever.
And the back and front wheels for in-city driving, your wheels turn this way and this way, in the front and the back. On the highway, they both turn the same direction, so you just kind of, the whole car would just slide back and forth on the highway, which would make it a little hard to get in between two cars if you can't turn your car like this to get between them if you're trying to cut somebody off. But, people shouldn't be cutting other people off anyway, so.
Yeah, that's still way cool, though.
Yeah, 4-wheel steering, 4-wheel drive. What was it? That guy was saying he could get around a street corner in a city at a red light at 60 miles an hour with barely barking the tires, meaning that he was losing almost, none of his control as he was going around because of the combination of the aerodynamics of the body, the fairings, and using the, 4-wheel steering and everything. Hydraulics too. Lower it down to, what was it? I think the lowest it got to the ground was like 3 inches from the ground for city driving. And then if you were off-roading, it would lift itself up like 7 or 8 inches. So you didn't get caught on stuff. It's not a whole lot. It's not a Jeep, but better than nothing. I'm like, the only thing they didn't do was use the pecan hull tires, where they use crushed pecan hulls to mix into the rubber. That way you get more grip, and instead of the 3,000 or 5,000 or whatever miles, I can't remember what the range of miles of the typical tire is, but this thing was those pecan hulls. They make them in Oklahoma too. Get like anywhere from 5 to 10 times the range out of them before they wear down.
Well, that's impressive.
Right, without losing grip, and it's because of the sharpness. That's what gave me the idea. I have 8 pounds of 150 grit silicon carbide back there.
Wow.
That and silicon rubber to make. I'm gonna try some boot soles first to see how well they work, see how long they last and whatnot. I'd like to be able to make a tire that lasts 3 million miles if you can drive it in 25 years, because that silicone will last a minimum of 25 years. And I think the black will last longer because the material that makes it black will block the UV from damaging the silicone. So it's a tire, though. If you peel out, you're not leaving tire on the road. You're literally kicking up the road and leave a polished groove in the road. So don't want to be basically peeling out. Probably go with bigger crystals on the outer side to get more grip too for wintertime and whatnot. So that way you can drive on ice and just dig into it with those little points.
Here's what I fashioned up. Basically, it's sheet metal. So it's just gonna be the.
That looks pretty cool.
What is that?
Nice.
Is that
Hope it holds.
Drive case?
Yeah, it's the cover of a hybrid battery computer. One of the defunct ones that I just took off the shelf here.
It's definitely steel, though.
Yeah.
What about galvanizing? There's no coating on it.
Yeah,
Just so it doesn't interfere, because now he's got me thinking about contamination, man.
Right. You always got to wonder. Hopefully it's clean.
Well, when he held that up, this is the first thing I thought of. That's a hard drive case, but this is aluminum.
Some hard drive cases actually are stainless.
This is definitely magnetic.
Right.
Well, that's good. At least it's not
That's
aluminum.
what I was wondering about the coating, though, because if it's galvanized, it would still stick to it because of the steel under it. Like, I've got a piece of galvanized angle that came out of like a plasma TV on my my shelf here that my TV or my monitors are on, because I use that for basically sticking stuff to it. It's all magnetic too, but you can tell it's galvanized because it's got that meteorite texture to it.
Yep. Well, here's my issue. Isn't actually that thing might be galvanized or not. It's that it's magnetic, and it might act like a magnetic shield for the bismuth that's about to be poured into it.
Oh, yeah. It's pretty thin though. It's going to saturate pretty quickly. What's the
I would
pattern of the
hope
magnetic
so.
field that's coming out of the magnet itself though? Like what shape is it? You know,
It's homogeneous.
that was bad. I'll have to get the glass cutter out and cut that down smaller. Man, I've had this thing for almost 10 years too. It was a salvage out of a scanner. Probably wouldn't have
I
broken
feel
it,
your
except
pain.
I got a piece of cut stone laying here on the floor that I use for like a heat pad to set my hot, food and drinks on and whatnot, so they don't burn my table. I should have put it back out there by the microwave where it belongs. That way I don't have to burn my hands to carry it back here and set it on it.
Well, it's too late now. The damage is done. There's no going back.
Yep. I have more glass around here, so if I need more, I'll go down to Dallas and get a shitload of tempered glass from Raymond. He used to do demo work and what do you call it? The commercial sheet wall, sheetrock hanging. He had a company doing that. That guy has got I think 3 or 4 pallets stacked up with 4 foot by 8 foot sheets of tempered glass mirrors. Had his people just pull them out without breaking them. Tossed the ones that broke. I'm like, man. He knows they're tempered glass too, because the ones that they broke, they literally broke into tiny little crystals. Just one drop, ruined, like a car window.
I can definitely understand exactly what you're talking about, man. I'm a glass installer, or I used to be at least as a part-time job. So I've installed a bunch of tempered glass and all kinds of glass sheets of various thicknesses, from 1/16 of an inch all the way up to about 3/4 of an inch thick. So the tempered ones, when you snap them, you just give them the tiniest little prick, and they will completely shatter into a million little pieces.
Yeah. Right.
It's awesome to watch, but terrifying. Don't be anywhere near it.
It's a lot safer because the shapes have, I guess they got more of an obtuse angle to them, so they're less likely to dig in and cut into you than say, something that comes out looking like a friggin' dagger,
Yeah, well, safer is a proxy. Trust me.
Right.
The pieces, as they're falling, then they're sticking together. They may not be completely shattered, and they will still slice off your arm. So
right.
Safe is.
or just grind it away and leaving nothing but muscle behind. Just strip everything down almost.
Yeah, I mean, either way, it's not a pretty
bone.
thought.
No. I'm glad I've got all the new diamonds, grinding and cutting stuff that I got for the tungsten. I got a bunch of tungsten carbide I need to shape for, cutters and whatnot. That used to be a drill bit, so it's served me quite well to do quite a bit of shaping and forming and stuff, because it's razor sharp, so it won't be that hard to cut that down. Actually, I don't think the last time I talked to you guys you saw this stuff. I forgot all about it. It's something I need to do some testing on. It's ruby and sapphire.
Oh, interesting.
So
I'm gonna cut this piece of glass real quick.
I would show you the fluorescent, but when I hit it with all of the UV that I've got around here, the whole thing just blares out so badly with purple color. You can't see that bright pink of the ruby parts like you can in person.
Oh, I understand what the saturation does, though, but I'll be able to interpret that as I'll still be able to see it. I mean, you can still see some slight fluorescence that'll come through and change the color of those pixels.
Yeah, it's not much though. It's really, really faint. I was compared to when I was taking even pictures of it with both of the cameras that I've got, looking at the pictures and looking at what I'm looking at with my eyes, it was just really disheartening that the camera was not able to pick that up to that even to a fraction of that degree. We're talking less than 4 or 5% of that other light is coming through, because it is the red is literally the maroon like stripes. They come out this really bright pink color whenever you hit them with the 405 nanometer and the 365 of the black light. So
that's awesome.
The blue just turns kind of black because it's not doing anything with it. There's some green in this too. I'm not sure what that's like, what the impurity is that's causing that, or if it's just because of the inference difference. So I've been reading up on heat treating. So at some point I should have a hot enough oven I can basically get this to completely fuse together and make like, unless there's something in there that will not melt at the temperature that the aluminum will, I should be able to get a completely transparent piece of material so it comes out like, what do they call them, party sapphires, where they have several different colors in one stone. So.
That would be super awesome if you could pull it off.
Right. Well, I was talking to Raymond ages ago about, you know what hydrothermal synthesis is, I'm assuming.
No.
You put like a decent sized chamber together, fill it with water, make sure it's sealed so it'll handle the pressure, and then you raise it to much, much higher than the boiling point, like 300, 400, 500 degrees Celsius, and it will actually dissolve the alumina. And if it's a big enough chamber, that means you'll have a temperature difference. I think the best temperature difference is like 20 degrees, because as it rises to the cooler region, it becomes super saturated and can't hang on to the dissolved alumina, and it will deposit to make a crystal. So you can grow a sapphire crystal. It's kind of slow, but my idea was to basically like shatter some of these so that we've got either that or make them like the guys that were using the carbon arc rods to basically, and they were using chromic oxide and alumina to make ruby material. Do that for both the sapphire and the aluminum. So you got the two separate, start with one, grow the crystal big enough, carve it into like a heart shape while it's still a ruby, then put it back in there and grow the sapphire over top of it. I figured it'd be, something unique enough. People would be very interested in it.
I think so. That's crazy awesome.
Get plenty of, funding for something like that. So.
I'm getting ready to pour here.
All right.
Just got to clean off the slag first. So. My slag cleaning tools.
Is that the kiln you guys were talking about that he's melting that with? Or
nope, that's actually a metal melting furnace. We have a different chamber kiln with the openable door.
Right. You said that it goes up to what, 1200?
Correct.
So that means it's not using Canthal A1, and I'm guessing it's probably got 2300 fire brick.
Yeah, it's nitro. It's very, very lightweight. It's very, very lightweight. It's kind of, I guess, heavy-ish, but it's kind of chalky. You can break it easily if you scrape the surface. You can chunk off little pieces of it. It's full of holes and porous, so it's a good insulating brick because of that.
Yeah.
They are using. I'm pretty sure it's
take
nitro.
Take a hacksaw and cut through it like you're cutting through like a piece of pine or a piece of
balsa wood. Easily, yeah.
It's really, really soft, and it's crumbly. Unlike the wood, it wouldn't bind up and create gumminess and whatnot. That's why I was saying that's the difference between this stuff and that. This stuff's heavier than crap, though. Like I said, I got so much of it. If you guys get the wiring, I could probably just have to figure out how to do the shipping, but send you guys enough of this stuff. This is that, I think they were saying it's like 30% zirconia and 70% alumina. So close to it. And then the tiny fractions of a percent left over are basically silicon dioxide, so impurities. But that's what they're using at the glass plant. So,
well,
and apparently it's not because of the higher melting temperature. It's because of the more resistant nature to the impurities in the glass to lower the melting temperature,
out.
The sodium and whatnot, because it literally dissolves the bricks away.
It's spilling.
These are looking like pieces of bone.
Yeah, it's coming right outside the holes.
Oh crap!
Yeah.
Well, we could have probably guessed. The cool thing is if it's liquid, it's still hot, you can just try to crimp those. Maybe you can seal it well. It's still flowing.
Did you roll the edge over?
Yeah, I rolled the edge, but apparently not enough.
Yeah, that's why I said the copper I think would have been better, because like I said, I'm able to get that to seal, but the steel I haven't been able to do anything with that. You definitely want to basically like put a weld on it or something to make sure it's completely sealed if you're going to do that. Or you fold the edges up so that way all of the, like you do with when you're using filters to put into a funnel, you're literally folding it up so that basically all of the edges are up
Now
on
I
top,
lost
so
power.
it can't go down and go out between the crevices because there are no crevices down low. But it doesn't look like you had enough material to even try that with that. Did you
Yeah.
catch all the bismuth so it didn't get all over the place? And
Yeah, it's all on that hot plate over there. So yeah, that's.
it looks like the same stone that broke my piece of glass, man. I'm just wondering what it's going to take to cut this stuff for, forming the cubbies for the coils, because I've got the first generation. I'll probably put Canthal A1 I've got here in it. So I've got I don't know, whatever that I think I got a pound and a half of 16 gauge Canthal A1. So, or not 16 gauge, 14 gauge. It's like a 16th of an inch in diameter, so it's pretty heavy. So it's thicker than the wire that's inside the kiln that I've got, because the kiln I've got sounds exactly like what you guys have got. I ran that thing for 2 hours at over 1,000 degrees, and it did not. I could still put my hand on the outside of it. The only place that was too hot to touch was the little hole cover, the hard ceramic cone that you stick in there to plug it up when you're not looking in there to check on it. I'm guessing that you guys have got the same features on the one you've got there, right? Let's see, what was that?
Okay, I got a little bit in here. Down, it's hardening inside the field, so it's not a total loss.
By the way, guys, since nobody has said it so far, and we've already passed it at 3:14 here. On 3:14, it is Pi Day. Happy Pi Day.
This is the first time I've actually known anybody else that actually recognized that or noticed that whenever it would happen.
Oh, don't worry. There's a very important reason why both Mark and myself and Jeremy are in full recognition of Pi Day and salute it greatly.
Know plenty of people that know about the March the 4th, but
How about May the 4th?
Is that it? Yeah, May the 4th, sorry.
May the 4th, yeah.
That's
when I filed for divorce.
I grew out of the whole Star Wars thing a long time ago whenever I started trying to make my own movies, and I didn't have the razzle dazzle of it. Had to have special effects, the best special effects. No, the story's more important. When I finally had an appreciation for Star Trek after my uncles had woefully given up on me, as a kid, because I just was like, nah. The manuals are cool, but the movies and TV shows, give me my Star Wars. I even like the Battlestar Galactica on TV better than that, so I was a little fucking turd, so. I'm assuming you can melt aluminum in that metal melting unit, right?
Yeah, gold, aluminum, silver.
Oh yeah, if you can melt gold, you can melt quite a few things, because that's 2,000 almost C.
No, it's 1,200 C, I think, for gold.
Is it? I thought it was close to 2,000, like 1900.
I think 2,000 is for
Copper's just like
iron.
a few degrees higher.
Iron has a very high melting temperature.
Right. Maybe I'm thinking of Fahrenheit. So,
Could be.
hold on. Let's see here.
You know what's interesting about copper? And I think this is true for many metals, actually. It doesn't really have a true melting point. It's more of a melting stagnation, where it like slowly comes into change in viscosity.
Right. Let's see here. Yeah, the bricks that I've got are probably in Fahrenheit. They're rated for about 4,300. At that point, they start getting a little worn from getting them any hotter than that. So 2,400 Celsius, something like that, without wear. But that's what I said. For brief periods, like an hour or two at 3,000, they should probably hold up. I'll just have to replace them after doing 2 or 3 runs like that. But I got so many of them. I'll just have. The trick is going to be the cutting. Like I was telling Jeremiah about, basically preparing the area where the coils for the tungsten will go in when I get that. After I pull the cantilever one out of it, I won't be working with a 1,400 degree workable temperature then. So I go all the way up to 3,000 if I've got the argon atmosphere. If I don't, then I'll have to stop at 26, or it's like somewhere between 24 and 2,700 degrees. I'd have to look. I can't remember what it was. I just know that no, it's like 2,400, because it's like 26 or 2,700 in a vacuum, which apparently no pressure means that it basically breaks down easier. It lowers its workability, or the point where the melting point starts happening, just like it affects the boiling point of water and whatnot. I really did not expect it, because I was like, well, there's nothing there to interact with it, so you don't have to worry about it oxidizing, right? But that's not it. You put the inner pressure on it from the argon, and it basically raises the temperature. You can work with it without it breaking down and melting and refusing to continue working, because you can't conduct any power. So the real trick is going to be standoffs and whatnot. If I can get a hold of some tantalum carbide wire for the filament, because that stuff, you can run that all the way up to like 3,800 degrees Celsius. So there's not much that you can't do with that level of temperature, other than if you're trying to make something like you'd make in a sun. We're not talking about millions of degrees. So,
Well, guys, I think I've got to run. It's time to make a mold for this thing and get back to the construction part.
all right. Hey, like I said, send me the dimensions you're looking for on that, even if it's the wire. I thought you were wanting something more solid too, but like I said, I'll dig around and find out what I've got, and we can move forward on that. Because like I said, drop that in a box and then see what you can do with it, man.
Yeah, if you can, we still have to make metal parts too, so we're looking for CNC machine capabilities that can do like millimeter-sized screws and whatnot.
Right. Yeah, my old CNC machine, I was able to hit on a 6-inch circular cut, I was able to hit like right around 10,000th of an inch. So, like repeatedly hit it the same exact spot within a 10,000th of an inch on MDF. I don't know what I can do with the ball screw system I've got back there. That was a polished 20 thread per inch, regular standard like screw system, and 200 step per revolution motors and whatnot. So motors are the same on this other thing, but the ball screws are probably going to knock all that off to where it's going to be much slower, but it still should be able to hit like at least 1,000th of an inch. So
One of these days I'm going to fix my CNC machine. I have a mini tabletop CNC that I built from scratch, and the problem I have with it right now is the spindle is constantly screwing up. It needs to be like force cooled, but I was trying to find a solution where I could just air cool it. Not going to happen.
Right.
So not going to happen with a high speed spindle. Have to. So I'll have to implement a new water cooling system on that and actually get a water cooled spindle, because I don't feel like trying to make a water sealed system from scratch.
you can probably pick that up on eBay. It's just a component to go on a CNC piece of equipment, pretty cheap. So
Yeah, I'm looking for a really
kit
small motor though, and a lot of them are
cheap.
huge.
Yeah,
I need-
that's true. That's true.
I really do need a kind of tiny motor. I was using those 3-phase RC inrunners because they're super small and they have huge amounts of torque. And if you can keep them cool enough, then basically they're going to give you those high RPMs that you ultimately want for millimeter, micro size cutting. Because I need the machine within 1/50th of a millimeter range.
That's not necessary to get that clean of cut. You need just basically rigidity, and you need to keep like some sort of lubricant on it, so that way you don't build up any chatter. You get stuff stuck to the tip. That's what I've found always causes all of my chatter and vibration and screws everything up. But if it's nothing sticking to it because I've got some oil constantly pouring onto it, or at least water, it tends to have no problem making really nice smooth mirror finishes and whatnot, even on a piece of steel. I mean, like I said, I was using channel steel like you find in the rack mount servers to attach all of the electrical on the inside of it. I use those for the rails, still have them back there. And then I was using MDF base angle iron to stiffen that to make sure it was perfectly flat and level. Aluminum blocks for all of the components to hold all the bearings for it. And it was like about 1.5 feet wide by a 2 foot long run that I could cut on any one part, using 180 ounce stepper motors. So that, and slow the movement of cutting around on things, that'll really, help out quite a bit too. But I mean, you as long as you're not getting any buildup, so that your cutter's going to get stuck in there and start trying to basically weld to the part that you're cutting. So sometimes slower could even be better. Slow the cutter down, but slow the motion it's cutting through. Make sure it's robust, so you can walk away and go get something to drink, go get something to eat, and not have to worry about it flying to pieces. And got your end stops on it. It'll take longer, but you can go work on something else while it's busy being that extra, slave labor in the shop.
Right.
We're using carbide bits.
All right, guys, I gotta run. I'll talk to you later. Chill.
Okay, guys, I think I'm going to stop the live stream now. You could stay on the Zoom call. I think we have some conversations we need to have off air as well. And thanks everyone who stuck around. We got 8 viewers left at 4:40 in the morning, so that's
that might be when you'll get most of your watchers, because they're basically night owls or something. Sometimes I get my best thinking done in the middle of the night, man, when no one else is around to bug the crap out of me. Because most everybody else just floods you with garbage.
Oh yeah.
Did you see what she was wearing? It's like, I don't care. It won't basically float her up into space, or allow her to make me a bunch of electronic components and zeolites to make food particles and stuff. So there's more important things to worry about, man.
There is a lot more. Everyone who's on the live stream, especially Peter, Middleton, and Esoteric Gold, guys, thank you for all the comments. Very helpful. Well, you know what? Before I cut it, let me just show you what the result looked like.
Did you get enough of it to stick around in there?
Yeah, there's a little bit that stuck around. Oh, it's actually cool already.
I wonder if the magnet cooled it off.
It probably did.
It's an interesting little effect. One reason I'd like to have a nice big chunk of praseodymium to work with. The magnetic heating and cooling.
Here, look at that.
Yep.
It got some weird shapes in there. I'm gonna pop it out and see what it looks like, and if there's any strange properties, I'll let you know. But
okay.
Everyone who's watching on the live stream, we're gonna end now for the night. Thank you for tuning in, and see you on the next one.